Hi, folks. You can go back and review if you wish to. So having said that, this is your warning. We're going to start this recording now. Okay. Now that we're recording, again, my name is Darlene Forrest. I'm the administrator of the New Hampshire Department of Environmental Services Wetlands Bureau, and I'd like to welcome you to session 2 of our September 23, 2022 training on protecting surface water quality on construction sites. This training will be or has been designed to be useful to professionals, environmental consultants, engineers, and wetland scientists. So before we get started and move on much further, we want to go over some troubleshooting, as this is a Teams meeting, which many of you, or Teams webinar, which many of you may not have used before. So for this, your camera for this presentation, your camera, your mic, and your screen sharing are disabled during the presentation. That's true for all attendees. You should see a toolbar at the top of your screen, which has the tools which the camera, mic, and share buttons have been grayed out. Next to those is a red hang up or leave button, which hopefully you won't need, but you may find useful just in case. If your meeting controls do disappear and you can't see them, simply move your mouse. They should reappear. If for any reason the presentation minimizes on your screen and appears down in the lower right or left-hand corner, simply click on the small presentation once and it should enlarge it again so you can see things in full size. If you experience any errors, you can leave the webinar by clicking on that red phone icon that I mentioned earlier and simply rejoin using the link. We'll let you back in. That's the quickest and easiest way to reset and correct any errors that you're having. And if you need any additional help, please email us at des.lrmb@des.nh.gov. So we will have Q&A sessions at the end of our instructional sessions and at the end of our presentation for today. During the question and answer, raise your hand, call attention to yourself by raising your hand using the virtual hand, clicking on the hand icon on the toolbar. So on smaller devices, if you're using like a cell phone or an iPad, the hand icon may be accessed through the ellipsis, the 3 dots, and then going to the menu. Once we see your virtual hand, we will take note of the order they go up in, and the meeting host, which I think is going to be me, will call you by name. And when we call on your name, your mic will be unmuted. It will no longer be grayed out. You will need to unmute yourself. We will activate your mic. It will become it will no longer be grayed out, and you will notice you can unmute it by clicking on your microphone button. So you will need to unmute that and help us out with that so that you can then ask your question. So having progressed through that part, let's get into our agenda for today. So today's agenda, 8:30, which would be, I don't know, like 5 minutes ago, we had the introduction by myself from DES. We're going to move on now to UNH Studies on BMPs Designs and Effectiveness, presented by Mr. James Houle out of the University of New Hampshire. Then we'll have a brief break. We will come back for a presentation on temporary and permanent construction BMPs by Mr. Shuey. And then after that, we'll have a wrap up that will be hosted by Ridge Mock of the Alteration of Terrain program here at DES. So with that, and moving right along, I'm going to introduce our first speaker of the day. Our first speaker is Mr. Houle from UNH. And our updated bio that Mr. Houle has given us. Mr. Houle is a grizzled stormwater veteran. In addition to directing the UNH Stormwater Center's growing body of research, he also enjoys water in the liquid and solid state, where the latter serves as a perfect medium for cross-country skiing and ice hockey. So with that, I'm going to cede this program to Mr. Houle. We'll make the screen available for him.
Great. Can you see the correct screen? Hopefully it's the full PowerPoint. Not the notes, okay, and you can see me and hear me.
Yes, we can see and hear you.
All right, then I think we're ready to go. Yeah, thank you, Darlene, and it's a pleasure to be here and discuss some of the current updates for different structural controls. Interestingly, if you've paid attention to the field, we now call them stormwater control measures. I don't know who controls the acronyms, but I guess this dates back to 2008 when the National Academies of Sciences produced uh, um, a report to Congress about the state of stormwater, and that's where they introduced this new acronym, SCM, which presumably replaces best management practices. Although you can never replace BMPs, it's kind of permanently within the stormwater lingo. I'm going to talk to you a lot about water quality and how to protect surface water from the impacts of stormwater. And it should be noted that now with the advancements on the wastewater treatment side, stormwater is now the #1 source of impairments for, at least in New Hampshire. I think it was calculated by the DES folks, about 93% of the problems with our surface waters is due in part to stormwater. So it's a emerging field, and the standards are ever increasing on the water quality side. So I'm going to talk to you about basically information that we've been collecting over the last 2 decades at our field facility. And we have moved on. You'll see data outside, but a lot of the initial information we collected over about 15 years of operation of our stormwater facility, which is located at the very corner of a 9-acre commuter parking lot. So it's equivalent to a commercial land use. It gets funneled into our testing area where we split it between various different BMPs. And hopefully these animations will play. Yep. So we did spend some time just developing fun animations just about how our facility works. So it goes into a distribution box where it's split between various treatment facilities. And, over the years, we've swapped them out for different types of devices. Water goes through. All of our systems are built in a very restrictive clay soil. So they're essentially, what we're measuring is a pretty conservative measure of a system performance. So we're not really taking into account any infiltration. And being built in a clay means there's really no interconnection subsurface between our structural systems. So it's kind of a great laboratory where we can study real hydrographs and real field conditions. So we don't modify the hydrograph. It naturally flows through our systems, and we get everything associated with the natural runoff patterns and the dynamic nature of those runoff patterns and pollutant loading on that commercial parking lot. So from there, water would flow into any one of our structural controls, and we do look at non-proprietary systems. We look at proprietary systems. We look at what we call now green infrastructure, and we look at conventional systems like retention ponds and detention ponds. So we cover the whole range. But water would flow into a system. It would filter through, be collected via an underdrain, because again, it's in a very restrictive clay soil, and then flow to our sampling gallery where we're quantifying effluent water. So the influent characterization versus the effluent characterization gives us our performance metric. And what do we look for? We look for the common stormwater pollutants, sediments, petroleum hydrocarbons, primarily in the form of diesel range organics or semi-volatile organics, and then nitrogen and phosphorus. So those nutrients really are what we are focusing on more and more these days. So sediment is relatively easy to remove, but the nutrients are really what we're seeing largely associated with a lot of our impaired waters now. So phosphorus in inland and freshwater systems, nitrogen on the coast and in estuarine style systems. And so when we look at the range of our data and the range of the different treatment practices that we've studied over the years, to us, a kind of a new convention emerged as a way to look at these types of structural controls. And by that, I mean using unit operations and unit processes, which are well understood and used in the other water utilities like wastewater and drinking water, in order to target pollutants of concern and get expected removal efficiencies from the effluent water. So there's really no need to reinvent the wheel functionally. Stormwater systems, even in a passive state, which most of our systems are, well, all of our systems. I don't know of many systems that have active recirculation or energy inputs. They're all relatively passive and gravity fed for the most part. There's these same unit operations and unit processes really apply and do the bulk of the work. And so, this would have made it a lot easier if we had learned this, and we should have known this in the beginning, actually. But we were largely distracted by all the cool names out there for these different facilities. And but I would say what we've learned is performance is highly correlated with the types of unit operations and unit processes that these systems employ. And in stormwater, we really have 4. So operations are more physical. So we have hydrologic and physical, flow alteration, and physical processes like sedimentation and filtration. And then processes are biological and chemical. And I'll go over those in a little bit more detail. I will take a time to note here that a lot of this information is embodied in a new retrofit manual that we were working with VHB to develop for New England. And it was funded through the SNEP network, which is the Southern New England program. That's a regional EPA initiative. And the SNEP network is housed out of the University of Southern Maine, and they funded the development of this retrofit manual. That's a lot of what we focus our time on, is retrofitting the already built environment in the Northeast. A lot of it is already built, and trying to reinvent, increase water quality controls for our impaired waters. And so I won't go over each of these unit operations, unit processes, but they're well documented. And we didn't reinvent this either. This is in all the wastewater treatment handbooks. And it's also in some of the more advanced stormwater manuals, like out of University or Minnesota, the Minnesota manual. And I'm just saying that for the most part, as you're approaching design, you work from the receiving water quality needs, right? So if you're in the coastal area, and we see this reflected in the AOT rules, as Ridge discussed last week, and we also see this reflected in the new standards that are coming out, forwarded through either the MS4 permits or where in the coastal region here in New Hampshire and the Great Bay, we're now the beneficiaries of a brand new adaptive management permit. So again, you work from the receiving water quality needs back to your system, and you make sure that you're employing these unit operations and unit processes that effectively address the pollutants of concern. So the reason why, and I think I mentioned this, but the reason why unit operations, unit processes really are make sense to me is that we don't get too distracted by the myriad of names and nomenclature that's out there to talk about stormwater treatment systems. So, whether they're proprietary or non-proprietary, I would say the proprietary systems really corner the market on the inventive names like, Stormtrooper, I like that one. Downstream Defender, I mean, who wouldn't want to defend downstream? But the names don't necessarily reflect the UOPs that are employed. And I'll say it just again for emphasis, but the UOPs really dictate expected performance pretty well. And so that's kind of the nomenclature that we're sort of going with now. And for me, it's very predictive. So if your target is nitrogen and someone's proposing a bioretention, we know that bioretention systems do well for nitrogen, but the major unit process in the unamended bioretention is vegetative uptake. You're relying on the vegetation to take up the nutrients, and that's a temporary sink. So those nutrients are held within the biomass for a certain period of time, and then, especially in the Northeast, during the winter, those plants are inactive. So that process is essentially shut off. And so we see pretty much the maximum end of the nutrient reduction capacity in bioretentions is around, conventional bioretention systems unamended would be 30 to 40% removal. Our targets now are much higher than that. So we're looking for 50 to 60% removal for most nutrients. And so we need to start amending these systems in order to meet those water quality objectives. And how do we do this? You already know, you use unit operations and unit processes. So it becomes much like your wastewater treatment plant, where you're doing primary, secondary, tertiary treatment, where you're stacking these UOPs to get the performance that you need. So a lot of these systems are employing the same process, although it's not as regulated and it's very passive in the environment. But we build these unit operations within our systems, much like you would in a wastewater treatment plant, sans minus the energy inputs and all that. So that's the new convention. And for me, it makes a lot of sense. And it actually, you can get kind of creative because I now look at BMPs or SCMs as kind of like a Mr. Potato Head, right? We know that infiltration, filtration systems do better. And now you start to stack these things and build it in order to incorporate the UOPs that address your pollutants of concern. So I'll just briefly go over those four EOP categories. So we have the hydraulic operations or hydrologic operations, sorry, that's flow alteration and volume reduction. So for the most part, volume reduction is a really heavy hitter, and we're seeing the standards around groundwater recharge or on-site retention being ratcheted up. And I expect that trend will continue. And right now, Massachusetts is considering a 1-inch retention standard, where basically the first inch of rain doesn't leave the site. So if you look at your toolbox, the best way to control that is going to be through volume reduction, through infiltration, or I think that's the main one. So you're slowing the flow down, you're enhancing infiltration when and where necessary. And that's not to say that this is infiltration everywhere. We have standards for where we encourage infiltration and where we don't. So something like gas stations or areas of high potential pollutant load, we don't encourage infiltration in those areas because we don't want to inadvertently create a groundwater problem. So I just want to say this has been a little bit misunderstood, and there's a lot of kind of anxiety around this move towards increased infiltration for those reasons. But we have standards and design constraints that regulate where and when we infiltrate. Physical operations, And these are the big heavy hitters, right? These are traditionally what we've used to control a lot of pollutants. Primarily is sedimentation. So any kind of detention or retention structure, this is the major unit operation. So a retention pond has a resident pool of water, a detention structure would fill up and then drain down to the bottom through an outlet. But there's no real infiltration component here. It's strictly sedimentation. So you're relying on that flow coming in to a quiescent area designed within the pond, and you're allowing natural settling and settling velocity of the particles to remove those pollutants. Enhanced sedimentation is something that I would use to describe hydrodynamic separators or swirl concentrators, any small system that would swirl water in order to enhance that particle settling. And there's physical limits to this process, right? This becomes physics, because when you're using hydrodynamic separators, and this has largely been this has already been proven over a decade ago, there's a limit to the particles that you can settle out. So essentially anything 100 microns or smaller, the smaller fraction of that particle range is not going to be settled out in a hydrodynamic separator that has a residence time of 2.6 seconds. So again, these unit operations present a really good framework in order to begin to understand the physics and the science behind pollutant removal. Filtration, and we see this in a lot of the local regulations that are being forwarded by the MS4 permits in Massachusetts and New Hampshire, are more and more encouraging filtration because you just can't get there or to the pollutant reduction requirements without some type of filtration component. And again, filtration, so that has to do with the media size, and the science is really balancing the media requirements in the media filters with the hydrologic response. So you're draining a large area. We want an efficient filter because we don't want it clogging, and we want to build in maintenance resiliency, but we don't want it so efficient, like filled with bowling balls or something, such that it doesn't impart that filtering process. Screening is something not so much used here, maybe in some of the urban centers, more in California, where they have a TMDL for 100% removal of trash. So this would be screening or filtering outfalls and outlets to remove gross solids and other floatables. As far as biological processes, we've got vegetation, and that's vegetative uptake, largely storage and incorporation of those pollutants within the biomass. And by far, like infiltration on the biological side, the game changer is these microbially mediated processes. So microbes live and prosper in these systems, especially when we create environments where that facilitates them and facilitates pollutant transformation. And so I would say in this instance, we're taking advantage of it to address nitrogen, and microbial mediation is the most efficient nitrogen transformation process, and that's permanent. Most microbes in anaerobic environments, or not most, certain microbes will, in the absence of oxygen, will take oxygen from nitrate and release nitrogen gas. So that's obviously nitrogen gas is inert and 80% of the environment or thereabouts. So it doesn't pose near the problem that oxidized nitrogen does, or nitrite. And then chemical processes. Here, we're largely looking at absorption, and so we've seen, to address phosphorus concerns, the implementation of phosphorus scavenging or absorptive components within these filters and enhancing that with media amendments. And so for in a lot of ways, that the two things that we'll talk about later that are really in our toolbox to increase sorptive capacity is use of water treatment residuals, so the polyaluminum chloride that's used in the drinking water treatment plant, and as a waste product generated from those processes, we're taking it, we're processing it, drying it out, and adding it as a soil amendment to some of our filters. And we're finding 20 to 30 year absorptive capacity for common levels of phosphorus in stormwater. The other thing we're using is iron and iron filing. So anything that has that metal ion and increases the cation exchange capacity of the filter media will increase phosphorus sorption. There's other proprietary materials out there as well. And we're just finding that because the hydraulic loading ratio of many of our filters, and when I say hydraulic loading ratio, I'm talking about watershed area to filter area, is large, so large areas draining to small filters. We really need to enhance the ability of that filter to work long term on some of these dissolved and more conservative pollutants. So the systems that we're really going to go over today are all systems that we've studied: retention ponds, swales and manufactured treatment devices, subsurface infiltration systems, bioretention in the range of media filters, subsurface gravel wetlands, and other, I guess, what I call innovative SCMs or different combinations of these. And I put retention pond in the yellow because, again, like I said, in a lot of the local regulations, we're shying away from these structures. While retention ponds can do well at removing the range of pollutants, if not maintained, they quickly degrade and then can turn into a source of pollutants. And they're finding that out now in Minnesota, where the land of 10,000 lakes is also the land of 30,000 historic retention ponds. And they're, of course, concerned about phosphorus, and they're seeing a lot of these retention ponds that haven't been maintained are stratifying. That how they're stratifying or why they're stratifying is still something they're looking into, but they feel it's possible it's somehow attributable to the chloride loading. But they're seeing release of this phosphorus. So these systems are becoming a source of that pollutant. So that's, the yellow is these retention ponds can do well as long as they have a healthy aquatic environment. Once they start degrading or once they start to eutrofy, they actually can become sources. And a lot of times that's due to lack of maintenance. Swales and manufactured treatment devices, a lot of the and I don't mean all of the manufactured treatment devices, but particularly the hydrodynamic separators are no longer really relied on for primary water quality treatment. So they can be conveyances or part of a treatment train or part of a 4-bay kind of pre-treatment, but they're not relied upon for long-term post-construction treatment. Subsurface systems and infiltration systems, again, where adequately sited, are really changing the game in stormwater. So that's replenishing groundwater sources, and it's also, for the most part, for things like phosphorus, infiltration is removal of that mass. Native soils are still very dependable to demobilize phosphorus. Phosphorus incorporates into mineral complexes and is not highly mobile. The two real caveats here with infiltration systems would be the dissolved pollutants of concern. So chloride, right? That chloride becomes an issue. So if chloride is your major pollutant of concern, infiltration doesn't always do, do the job. And in some cases, especially abutting sensitive streams, it can actually delay the plume so that the chloride plume is releasing when the biology is more active, as opposed to in the middle of winter when, you know, maybe some of the biology is not so active. And then nitrogen or nitrate. So, you know, here in the coast, we rely on infiltration for nitrogen abatement. But in the Cape or in these sandy environments where groundwater travels relatively fast, they give virtually no credit for infiltration for nitrogen reduction. And so it's what we're really keying into now is the fate and transport of nitrogen. So on the Cape, if they're giving no nitrogen reduction credit for infiltration systems, we know that that's probably not right. And 100% is probably not right as well. So we're somewhere between 0 and 100, most likely. And again, it's going to depend on where you are in relation to your impaired water. Bioretention systems are really the workhorse of many of our structural controls. And in New Hampshire, they're relatively easy to implement. So it gets difficult as you go to more and more urbanized areas. So bioretention is much easier to site and install in Durham, where I live, and difficult, although doable, in urban environments like Boston. So, you know, a lot of these have, so really we need the range of systems and at our disposal. Subsurface gravel wetland systems are probably the best performer across the range of pollutants. However, they require a lot of space. And so we're starting to incorporate the different components that saturated zone in the subsurface gravel wetland that does so well at mediating nitrogen into other systems, and I'll talk about that a little bit later. And that's really where we get to the innovative SCMs, where things that we haven't thought about, things that are relatively simple, and things that are emerging to meet the increasing demands on stormwater designers. All right, so I'll go into, let me just check time. So I think I'm done. I've got another hour and 25 minutes, and I only have 425 more slides, so I should be fine. So retention ponds. I talked a little bit about retention ponds, and you know, they can do well. They have a history of not doing well and actually being sources of pollutants due to lack of maintenance. So the maintenance of a retention pond is going to be difficult. A lot relies on the pretreatment, whatever that is. Previously or historically, we focused on pretreatment as being a structural forebay. We're becoming a little bit more flexible as, again, we have constraints, environmental constraints on that, on how we're doing pretreatment. Oftentimes, say, you know, a great use for a hydrodynamic separator is upstream as a pretreatment structure for a downstream water quality system. So the design of retention ponds haven't really changed that much. You have multiple outlet structures, you have a resident pool of water, and really the performance is enhanced by the runoff coming into that kind of quiescent pool of water. The idea is that pool of water does a better job of slowing everything down and giving those particles time to settle out. But as I've said, over time, if not maintained properly, these things can really become not only unsightly, but sources of pollutants. And we've now since adopted many of the performance curves that are in Appendix F of the New Hampshire and Massachusetts MS4, and are also available on our website, also available in the new retrofit manual, where a lot of these performance curves, the way they've been developed is through continuous simulation of our rainfall record. And that rainfall record is ever increasing. I think we're up to 29 years now. So that 29-year rainfall record is simulated in SWIM, which is a pretty robust hydraulic model. And the water quality performance is calibrated a lot by some of our historical data. And what's generated is this curve or performance curve that shows essentially a physical storage capacity, which in some instances is much like a design, a water quality volume. So physical storage capacity is the storage capacity in the system for water as it relates to the drainage area. So, you know, for most of our systems that we're designing for new construction and redevelopment, that criteria is 1 inch. So you size for the 1 inch rainfall event, and that would be somewhat, and that's typically a statically sized. So 1 inch of rainfall generates a runoff from your drainage area, and you kerplunk it in your system, and your system's designed to statically store that water quality volume. That's essentially the same as what the curves are referring to as a physical storage capacity or runoff depth from impervious area. So we do have some new acronyms to learn as we begin to access these performance curves that EPA has provided for us. The beauty is once we kind of shift over to this new way of doing things, one, it's not that different than how we're already doing it. And we have access to a growing body of research around these performance curves. So when we started when the mass permit came out, there was sediment, there was really just phosphorus. Now, as the New Hampshire permit came out, we have sediment, we have phosphorus, we have nitrogen. We've recently developed curves for bacteria and metals. So as we build out these performance curves and calibrate them, since you're using the same kind of nomenclature and it really doesn't tell you how to design the system, you design the system according to the updated standards in your area, but every design system has a physical storage capacity that can be easily calculated. And we're not going to go into it. We have whole courses and lectures on how to do that. And I'm sure that will be rolling out as this accounting and tracking component becomes more and more prevalent. So as I said, in the Great Bay area where the beneficiaries of a new permit, this is a really important part of demonstrating that municipalities are being accountable to meeting the requirements at the receiving water. So swales. We've experimented with a range of swales, and swales can become very sophisticated, right? So in Connecticut, I always used to get tripped up because in Connecticut, they have a water quality swale, which is not a trapezoidal channel. It is really a linear bioretention system. And so this is where, again, the UOP nomenclature really can benefit us. If I'm designing a linear swale with a shallow slope and filtration media, and I'm enhancing storage in that in order to enhance filtration through a engineered soil media and infiltration back into the soil, then I don't really have a swale anymore. I have a linear bioretention system. And again, no matter how I design that, I can still develop a design storage volume and a physical storage capacity, and I can get access to these crediting and accounting metrics. So, you know, the ditch or the trapezoidal channel with a certain slope is really a simple conveyance device. And if it's not enhanced beyond that, you know, that's what it gets credit for. And there are curves for grassline swales. So, you know, swales, again, are likely not going to get you, unenhanced aren't going to get you primary treatment, but are great as pre-treatment and great for conveyance. And can also be good in a linear transportation environment. So, you know, if you have a highway and you have a median strip, you know, those swales where you can direct water to, the hydraulic loading ratio is very, very low. So you have a small area to a large treatment area. And there are new standards for what is called impervious cover disconnection. And that's really what it is. It's a kind of matching a hydraulic loading ratio that's relatively low. And there's now performance curves that Rhode Island DOT has developed as part of their consent decree that have been incorporated into this scheme, this accounting scheme. So hopefully you're starting to get the picture that, you know, the picture of the fabric of post-construction stormwater management is a little bit fluid. And as we enhance the capacity of our system with this kind of unit operation and unit process approach, we are kind of going beyond the traditional naming convention of our styles of the conventional nomenclature that we've used so effectively up till now. This data is from a unenhanced trapezoidal vegetated channel, and we see that it doesn't get much with respect to peak flow reduction, and the water quality performance, again, is modest and wouldn't qualify as primary treatment according to the latest standards. But again, you should already kind of start being able to assess the performance expectation you have just from how sophisticated or unsophisticated the treatment structure is. Hydrodynamic separators, I won't spend much time. You know, I think the genie's out of the bottle. I think a decade or so ago, there was a lot of hope that hydrodynamic separators were going to solve our problem. They're easy to install. It's just the primary unit operation is enhanced settling. And enhanced settling really doesn't get you that much with respect to water quality improvement. And we actually see, interestingly enough, we actually see impacts from cold climates. So if you think of a particle settling, as the viscosity of the water goes up, say in the winter, that the particle settling time pretty much doubles between cold water and, say, warm water. So those things are at play too. And for the most part, the residence time of these systems are in seconds. So, you know, if you just think intuitively, you know, a quick swirl, a two-second swirl of the water, what are you going to remove? You're going to remove big stuff and coarse material. So it's great for pre-treatment, not great for long-term treatment. All right, subsurface systems. So there's a range of these, and they range from proprietary devices like chamber systems and infiltration chambers, big, large diameter perforated pipe, to stone systems. And again, what the chambers are actually doing are creating a structural void space. So for the most part, 3/4 inch stone, we calculate about a 40% porosity. So you get a 40% void space. Here, if you're using this chamber, designed appropriately, it can be supportive of transportation above it. And it can give you 100% porosity within the bottom of this chamber. So whether it's pipe or whether it's chambers, whether it's milk crates or whether it's concrete or whether it's galvanized or some type of corrugated metal, what you're creating in the subsurface is storage. So for the most part, stone in our area is still relatively cheap, and we can get the storage capacity that we need in the void space of the stone without too much trouble. As you get into urban areas and as you get more restraints as far as space, these things become very profitable. But the function is very, very similar. So this is essentially, you have an underground storage capacity, and you're really relying on infiltration into the native soils to do your primary treatment. A lot of these systems have like a first flush component. So with a chamber system, there's a first flush chamber row where it takes the water from the initial flush, I think in some systems it's called an isolator row. So it's just a specialized row of your chambers that has additional water quality controls. So you can see it here in this picture. We have a woven textile on the bottom, and it's kind of wrapped in a fabric around it, in a non-woven fabric. So water comes into the chamber. Oh, I think I have a video. Water comes into the chamber, filters down through that woven fabric, and that creates kind of like this filtration component. Woven fabric we find that in the field, woven fabrics are more reliable for infiltration, and they're also stronger. So the maintenance here would be you stick a hydrojet in the very back of the system. So a hydrojet gets propulsed to the back, and you drag it along that woven fabric layer and scour the sediments back to the sump where you vacuum them out. That would be the maintenance. So again, whether it's a stone in the subsurface system of a permeable pavement or whether it's a chamber, the function here is very, very similar. And we start to break up system and system components by their maintainability. So subsurface systems, the really Achilles heel is oftentimes, if it's underground, it's forgotten about or more easily forgotten about. And contrast that with a bioretention system that I can drive by after a rain event, and I can visually assess it and understand whether it's functioning or not in minutes. So this requires a little bit more in-depth inspection. And again, the long-term maintenance is a combination of vectoring and hydrogening. Hydraulically, all these this works much like an underground pond. So you have large storage capacity, an ability to infiltrate into native soils over time, which dampens peak flow and improves water quality. So whether it's chamber, whether it's, again, any type of system, I throw subsurface gravel filters in here. I throw porous pavement. The only difference is the hydraulics, like the inlets and the outlets. There's also manufactured filtration systems. And there's emergence of cartridge filters as well, or ribbon filters. And so these would be more proprietary systems that use some type of media in order and some type of modular subsurface system to filter the water. And the expectation of these all come down to the characteristics of the filter material. So whether it's a perlite or something innovative like a zeolite or an expanded shale, or it could have all kinds of amendments to it to help boost the performance. Or whether it's a fabric or a ribbon style filter or cartridge. The long-term prospects and the maintenance burden all reflect back to the characteristics of what that primary filter media is. So coarser filters like expanded shale or perlite will have high infiltration rates. And it's possible they won't get as good performance initially, but also might have longer maintenance or longer periods in between maintenance regimes, because there are some planned you're installing a high capacity filter in the beginning, you're planning some reduction of that infiltration capacity over time, which then enhances the filtration, as opposed to maybe a ribbon filter that might get good filtration from the start, but may have to be watched closer as everything begins to clog. The performance capabilities of these types of filters are good. So we know that manufactured treatment systems can do well. The limit here is probably nitrogen. So again, this is data from our site, and I'm showing you removal efficiency here on the vertical axis, and the horizontal axis of the range of pollutants. TSS is sediment, total petroleum hydrocarbons, those are semi-volatile organics, total zinc, dissolved inorganic nitrogen, that's ammonia, nitrate, and total phosphorus. So you see this kind of blank spot here. And if you're using this kind of new machinery of unit operations and processes, there's no anaerobic zone here. There's no real spot for vegetation, and there's no question why there's a limit to nitrogen reduction. That doesn't mean you won't have some reduction based on infiltration, because a lot of times in the performance curves, you'll see that the systems that infiltrate are the top performers. And the assumption there that once it goes in the ground, that pollutant disappears, or that pollutant that's 100% mass removal. And, that's the assumption we're dealing with now. And I said earlier on, hopefully, that it's pretty consistent for sediment and sediment-associated pollutants like hydrocarbons, metals, and phosphorus. But where it breaks down is chlorides and nitrate. So this is where we have to plan for the receiving water needs in our design. Subsurface infiltration systems, there's two performance curves for these. One's an infiltration trench, one's an infiltration basin. They're very, very similar. A trench is longer than it is wide. That's the primary definition. And depending on where you are jurisdictionally, may require at least a listing of in some jurisdictions consider it a class 5 injection well. So it goes on a list somewhere, not in New Hampshire, but so, but no real difference from a performance perspective. So bioretention systems and other media systems, now it's really all attributable to the size of the system, that hydraulic loading ratio. And we see in some jurisdictions, they limit the hydraulic loading ratio for bioretentions. Like in Maine, it's a 20-to-1. So for every 1 square foot of filter area, you can only drain 20 square feet of watershed area. So that's a hydraulic loading ratio of about 5%. In a lot of our installations, it pushes 100-to-1. But That's going to be a characteristic, and that's largely going to determine maintenance burden. And then the larger your hydraulic loading ratio, the more infiltration capacity you want in your filter. So for a lot of the proprietary tree filters, these are small areas that drain larger drainage areas, and they're pushing infiltration rates upwards of 100 inches an hour. So we don't see that most in bioretention systems. For the most part, if you follow our spec, which is online, we see an installed infiltration capacity between 40 and 60 inches per hour, and that's fast. It's a sandy soil, and so sometimes we struggle with, the sandier the soil, the more filtration you're going to get, but you're going to struggle with the vegetation. So the sandier the soil, the harder it is for the vegetation to hold. I think early on we didn't consider fertilization of these systems. Now I think some initial fertilization just to get the plants established is fine, as long as it's low, and it's better to me than putting large amounts of compost in your mix. And compost, not only is there no real definition for what compost is, there's a broad range of what that actually is. Just like loam, just like sand, these are terms that, at least in the public space, are not well defined. Certainly in the DOT environment, we have the AASHTO specifications, and we rely on those a lot in our specs in order to target the type of what we mean when we say a sand. Yeah, for the most part, we don't incorporate compost in nutrient restricted areas because we see a lot of export of when compost is used. So that can be addressed by these media amendments, but we have to be careful. So I think University of Vermont has already also shown this, that compost as a component of your bioretention soil mix has the potential to leach phosphorus. So I think what I was saying is I'd rather see you go with a no compost mix, and we use about 20 to 30% loam and do an initial fertilization to get the plants going than to use a compost for long-term plant support. And that has the potential to leach. So these systems are relatively easy. It's a soil media, and for the most part, we focus on the engineered soil media. I'm not a plant specialist. I know that there are certain species of plants that hyperaccumulate pollutants of concern. I'm not an expert in this. We like stable vegetated systems, and I've been pretty agnostic about what that is. And so you'll see the space here. There's not a lot of research on the plants and the long-term performance. We know that plants have all kinds of added benefits. We know they sequester carbon. We know they provide habitat for pollinator species. We know they enhance the beauty of the environment, right? And we know long-term they're required for these types of systems. What's difficult to say is what's the difference between a grass system and, let's say, in an urban environment, and a system with like diverse native vegetation, from the typical water quality constituents and from the hydrologic transformations that are going on here. We see that they're very similar. And I don't want that to be misconstrued. Usually cue the rotten tomatoes being thrown my way. I'm not saying that. I mean, you need to design the plant palette that is most likely to get maintained. So that's the key thing. And this is and I come from my school of thought on this is we need a big umbrella because we need more BMPs. We need whatever you're going to do and whatever you're going to maintain, I will take it because that's how far behind we are on a lot of this. So in most transportation environments, you know, grass, we use grass because that can be maintained. And from our research, that's fine. So I'm gonna, there are performance curves for biofiltration. There's a little nuance here that I should cover. Biofiltration is different than, I'd called it bioretention, or biofiltration refers to only the treatment of that actual filter system. So in this particular performance curve, you're not getting attendant reductions from infiltration because the idea is that you're not infiltrating. What we have negotiated with EPA and will become and is in the retrofit manual and will be coming out in hopefully other manuals as they update throughout New England is if we're designing the underdrains such that we are elevating them and not putting them in the bottom of the system, we're elevating them to enhance filtration and infiltration, then we should be getting credit for the infiltration capacity of the system. So for the most part, when we model a bioretention system and we elevate the underdrains and it's in a decent soil, like an A to a C soil, we're modeling as a infiltration basin because we're taking it credit for the infiltration that we know is happening. So you would use the biofiltration curve when you're in a D soil or you're in a soil where you're not anticipating it infiltrating much. All right. All right, now we'll cover the subsurface gravel wetland. And this, as I said, this is kind of the workhorse of at our facility. So we've researched this over time, and this has been the largest or the best performer for the range of pollutants. And essentially, it's a horizontal flow subsurface wetland. So water comes in, there's some type of hydraulic inlet to the subsurface, and water's treated through the stone reservoir that spans these different bays. Traditionally designed subsurface gravel wetlands have 2 bays, both sized at 45% of the water quality volume. And then you have 10% of the water quality volume in the pretreatment or the 4-bay. That's conventionally how it's sized. Over the years, we've been asked why 2 bays. And, you know, I think in the stormwater world, we suffer from just the sheer lack of research that's out there. And we say 2-bay gravel wetland because that's what we installed and that's what was tested. We haven't tested a single bay gravel wetland. My expectation is that a single bay would function in a similar fashion. We just haven't researched it. So, you know, over the years, certainly this has been probably one of the largest topics of discussion with the AOT program because they reference subsurface gravel wetlands as specified by the UNH Stormwater Center, and our specification calls for 2 4-bays. My opinion is that I would rather see a single bay subsurface gravel wetland than a, say, a retention pond. From a water quality perspective, I'm much more confident in the treatment capacity of a single cell subsurface gravel wetland than a retention pond. But again, we have to specify and we have to stick with the data. And sometimes that's a benefit because we can advance based on the recent science, and sometimes that's a restraint because we have to go with what we study. Hydraulic performance of these systems is high, and it's because you have a large footprint. You have a small primary orifice control that regulates everything. And so that's what you're seeing here. It's just a subsurface orifice that is metering that flow out constantly over the storm period. And the performance curves for these are good. However, you're gonna say, oh, why isn't it as good as the infiltration basin? And it's because in general, a subsurface gravel wetland designed and sited appropriately will not infiltrate water. If you have good soils, you will want to go with something else, and we have developed that, and I'll talk about that a little bit later. I'll talk about that right now. So I mentioned a little bit about Mr. Potato Head, and this is what we've started to do as we find gaps in the structural control measures. We fill them by the current research. And so we have worked with AOT pretty extensively in these areas that Ridge said require additional treatment. So in the nitrogen and phosphorus impaired watersheds, we have what AOT requires is essentially the limit of technology. So they're requiring a subsurface gravel wetland, and we've actually worked to develop a hybrid system, a bioretention system, because the worst thing in my mind is disconnecting from good soils and that infiltration capacity and that hydraulic balance or hydrologic balancing that you get from treatment in good soils by lining it. So we worked with DES AOT to develop a hybrid system that could meet the enhanced requirements in nitrogen impaired areas. For phosphorus, they're using these media amendments, so primarily water treatment residual and covalent iron to up the scavenging capacity, the absorptive capacity of the media for phosphorus. Chloride, we don't have much for you in the structural control measure category. There is, this is from once chloride is dissolved, it's very, very conservative, very hard to take out. So source control is really the biggest winner here. And we're very fortunate in New Hampshire to have a very innovative, very effective program to control the source of chloride, and that's the Green Snow Pro program. So pretty special, pretty unique here. New Hampshire is really leading in that category throughout the country. And the Green Snow Pro, I think, is the best approach to chloride control, because from the structural side, we don't have a lot of tools in the toolbox that are inexpensive, passive, and gravity fed. And that's, I think, what this slide is about. So yeah, we generally like the source control strategies, such as advanced by the Green Snow program, the equipment calibration, the weather monitoring, and we know that DOTs are doing this to the maximum extent. And also brining, that has become really a really important tool in the toolbox for chloride reduction. For nitrogen and phosphorus, the Ridge went over this last week. It's really, we're trying to meet anti-degradation. So while AOT directly isn't requiring pollutant load calculations or the load balance, what they are saying is you demonstrate anti-degradation by using these prescribed devices. So for nitrogen, it's a subsurface gravel wetland or a hybrid bioretention system, which I'll go over later. Or in the phosphorus areas, it's some type of enhancement. And the tools that we have right now are the water treatment residual and the covalent iron. And of course, you can use infiltration to the extent that you can, but all these include infiltration and filtration components. So I think Ridge went over this last time, so I'm not going to go into it. It's really, you know, if you're discharging in a watershed that's impaired for phosphorus, then you need to install a system that has that phosphorus enhancement. So a filtration system that has phosphorus enhancement. In the coastal area, if you're discharging to an area that's impaired for nitrogen, you're needing to add that saturated zone that mediates the nitrogen microbially. This is also being advanced in the MS4 in the same areas. So, you know, the difference is AOT advances kind of a limit of technology. So they pick the best performers and say, do this. And what EPA does is it says if you're doing installation in these areas, then you need to basically demonstrate by this accounting metric meeting anti-degradation. So it's only in select areas that apply, that have a TMDL or water quality limited. So it's not everywhere, but it's in these select areas. And you see we're moving kind of in this direction for more accountability. And we expect with the new MS4 that will come out, you know, it'll be even more prevalent in the permit. And we see it in other permits, such as the Great Bay Total Nitrogen General Permit. There's full accountability in there. And there's a benefit for accounting. One, we have the tools. We can do this. It's relatively easy. We have standardization of these metrics. And so there's really no limit to doing this. We have the tools. We have a program in the Great Bay called PTAP. That's a pollutant tracking and accounting program. And EPA has a software called the BAT, the BMP Accounting and Tracking Tool. And I know that VHB has done a lot of work with RIDOT and MassDOT, who both recently signed consent decrees using these same metrics. So throughout New England, we're really kind of migrating towards the same metrics. So the accounting is very standard and the same throughout. So, I'm going to talk about nitrogen reduction first, and then I'll get into, and I'll talk about the hybrid bioretention, and then we'll get into phosphorus next. And I'll just show you some of the background information. For nitrogen, really, it's gravel wetland. Again, it's our top performer. We have done some innovations, largely through studies that DOT has conducted and studies that we've been conducting long term. This is all on our website. If you go to www.unh.edu/UNHSC, we have a page that's publications, specs, and info. And we have all these specifications in detail there. And we update them as we come across new improvements. So a couple of the new improvements we have for gravel wetlands is we've kind of taken away the early constraints of length to width ratio that really constrain their use in the linear transportation environment. So to as far as we can tell, the length to width restrictions really was a tag along from old retention pond designs. And the idea was, we used to have a requirement that the length to width ratio was 0.5. So, the system is twice as long as it is wide. And sometimes you see that in ponds as well to help disperse the flow. And we really didn't, as long as you have that 30 feet of gravel travel, which we think is the most operative piece here, we feel, confident that we can take away that length to width ratio. And we do have studies on linear gravel wetlands that don't have length to width ratio of 0.5. and they do just fine. So, you know, that was one of our first amendments to our gravel wetland spec. And again, we think it was something that was just a carryover from old specifications, and this is kind of how things go in the stormwater world. You know, assumptions on top of assumptions, and where we can and we can make it more flexible, we try to do that. The other thing is the hydraulic inlet. So high water gets into the subsurface. We used to use a perforated riser. These can be areas for high maintenance, right? If those perforations aren't slotted appropriately, or it's possible they get clogged easily. So we've added primary hydraulic inlets, essentially, which is a spillway covered with a 4 to 6 inch diameter stone underlain with a woven fabric. So that creates an instant kind of right at the inlet, hydraulic inlet. We often use the perforated pipes as a secondary hydraulic inlet, and this just gives us belts and suspenders. The idea here is, you know, this system needs to be maintained when essentially the wetland has sealed itself off from the subsurface. And the maintenance here is cleaning or washing of the perforations of the standpipe, or replacement of that woven fabric under the 4 to 6 inch stone. So the 4 to 6 inch stone is really just a riprap apron, and it's underlain with that woven fabric, which can be taken out and replaced. So in environments where you have good soils that are appropriate for infiltration, we have adapted what we call a hybrid bioretention system. And essentially what this is we've Mr. Potato Head in a primary flow path through the bioretention system that is a gravel wetland. So it's like a nested gravel wetland within a larger bioretention system. And the idea is that primary flow path is kind of like a bathtub. So the first flush, and we know that especially dissolved nutrients like nitrates that probably are landing on surfaces from emissions from vehicles are mobilized really quickly. Like we often talk about first flush. These are much more first flush influenced because they easily dissolve and are mobilized in water. So the rainfall comes, that initial plug that has the majority of the soluble nutrients in it goes through this primary flow path, which is essentially a nested gravel wetland within a bioretention. That bathtub operates much like a gravel wetland through the primary first flush flow path. And as the system fills, that bathtub fills and it spills over into what is a conventional bioretention system. And now you have treated the first flush flow path, and now subsequent flows can have the ability to infiltrate into the good soils. So I apologize, I don't have cartoons outside of these CAD schematics, which I know can be somewhat hard to digest, but I kind of explained it in a nutshell there. The key here is within this first flush flow path, which is a gravel wetland in a bathtub. So that means that it's lined with an HDPE liner or other compact soil liner. You have a secondary liner that is placed in an adverse slope back from the outlet. So that's back from the outlet. And then, and what that does is it creates a very circuitous flow path. So, and with that, we don't get short circuiting close to the outlet structure. So again, the outlet structure is what governs a lot of the hydraulics of a conventional gravel wetland system. And we don't want water that's being infiltrated because we're using a more permeable filter material. We're not saying, you know, do something different on this surface. in a gravel wetland spec really requires a low conductivity muck layer. So the wetland soil has certain properties that essentially over time it seals itself. So you're not getting vertical infiltration in a gravel wetland through the soil. The vertical infiltration is going through the inlet structure. So here, because you're using a more porous, more amenable filter media, we're adding this adverse sloped liner, which means as the water vertically infiltrates, it's hitting that liner, running along that slope, and maximizing the flow path through the anaerobic zone. So hopefully that's clear. This has been done. I had wanted to get out and take pictures of it. There's one installation in Barrington, and this was passed through AOT, and it was done on a residential subdivision, and there were really good soils. So you can see this little T pattern here is our first flush gravel wetland. So essentially, we're collecting water within the basin from the forebay into this infiltration zone, and then it's being routed through the outlet control through this gravel wetland section. So this is essentially the gravel wetland component. As that fills and spills over into the sides, it's functioning like a traditional bioretention and taking advantage of the B soils that are here and getting that added benefit of volume reduction. So really kind of a cool idea such that we can continue to utilize good soils for that volume reduction. So a quick schematic of what that looks like. We have monitored one of these. We've installed one of these on the Cape. And again, the Cape is that old glacial outwash or moraine. It's full of good conductive sands, and they have nitrogen issues. So when we installed this gravel wetland, essentially what we have throughout the primary flow path is this lined gravel wetland, and then as it fills up and spills over the side, it accesses those good soils. So the way this functions is almost 100% like an infiltration basin, but we get that first flush flow path and we get the nitrogen treatment. And we've been monitoring this, and we see about a 90% volume reduction. And so that's really great. You wouldn't expect a 90% volume reduction from a conventional gravel wetland, but we do from this hybrid style approach. And you can see so here, just like the inlet that I showed you in the cartoon earlier on for the gravel wetland, we see a very dynamic inlet hydrograph inspired by the rainfall pattern. Rainfall here is in the right-hand vertical axis, flow is in the left-hand vertical axis, and then we just have a storm event. The outlet is really shown in green. So that's that first flow outlet. It picks up early on, and it kind of meters that flow out through the primary flow path. And then you have bypass, again, which is spilling over the sides and getting into the infiltration area. There's just another storm event. So this system has the ability to respond to very flashy storms, but it also has the ability to route that nitrogen. So, we see high spikes of nitrogen concentration within our system. So this is real-time monitoring, again, from a storm event. Essentially, this is a pollutograph. And then we see very controlled outlet concentrations for sediment, for nitrogen, and for phosphorus. When we look at this cumulatively over time, we see a really good, really good nitrogen levels coming out of the outlet. So, and really good volume reduction. And I think I have, here are the nitrogen reductions. So I guess we'll focus on the total nitrogen. So essentially the median is about 86% removal. So that's right on par with the median values of our historically monitored gravel wetland system. So 86% removal for nitrogen, 99% reduction for phosphorus, 99% reduction for sediment, 90% volume reduction. So it's doing good across the range of pollutants of concern, and it's certainly meeting all of the most up-to-date requirements that we're seeing come through the different permits. So that's the good news for phosphorus. I said we're really kind of focusing on these immediate amendments, and this is based on some studies we did, column studies we did early on, where we looked at a range of different promising media amendments and really focused on two: the alum sludge, so that's the water treatment residuals, and the zero valent iron. So limestone and slag really didn't do much. And I'll show you the data. So essentially, these are box and whisker plots where we had from our column studies where we put phosphate in. This is the control. We targeted about 1,000 micrograms per liter. And then here's the range of performance across all our different mixes. And so when you look at the water treatment residual, we look at them in various levels. So with 5%, that's 5% by volume versus 10% by volume, and then 3% by volume iron filings versus 6%. And we're, since this is a logarithmic plot, it's a log scale plot, we're increasing an order of magnitude in every line. This performance is it certainly separates itself from the other systems, and it's really all in line. So there's not much statistical difference here. So we go with about a 5% recommendation for a 5% water treatment residual volume and a 3% covalent iron. Those are the regulations or the recommendations for phosphorus optimization. And I can make this report available online. So coming into the home stretch here, I wanted to talk briefly because I know there was a question about the New Hampshire Stormwater Manual. We've been waiting for 14 years for the update, and it's finally coming. So we are working with CEI UNH is working with CEI to update the Stormwater Manual. CEI had conducted a previous study where they consulted with a focus group of a range of end users, and just to collect feedback on the manual and certain points where that might need update. And so really the points that we're going to focus on is, it's likely going to be an online document. It's going to be housed at the University of New Hampshire. It's going to, we're going to be considering how detailed the BMP designs should be. So we know there's continuity issues sometimes between the existing manual and the Chapter 1500 rules, and we want to do our best to kind of reconcile that. That's really what this content piece is about. So we want to reconcile the incongruencies between the MS4 permit, the construction general permit, and the Chapter 1500 rules with the updated manual. Easy, right? No problems there. So yeah, we're going to have our work cut out for us. And we're going to add updated BMPs, such as the ones that I just went over. And we're going to look at other things, such as what do we do for rainfall, and what do we use for rainfall? What do we use for climate change projections? How do we incorporate these performance curves that EPA has developed and are included in the BMP accounting and tracking tool? Another big thing is how are we going to update this recharge volume? And fortunately, Massachusetts has been going through this, so we will be able to benefit from, their path for updating their manual, and CEI also did that. So that's kind of what's in the mix now as far as the timeline. We just kicked the project off, so the goal is to have it completed by next August. And I know there was also another question about public engagement, and we do have sections for public engagement. So we will kind of vet the decisions that the in-house expert panel has developed with respect to those questions I posed earlier, and we'll be able to vet that over the process of the manual development with public comment and engagement of end users. So I am just about finished, and we have ample time for questions. So hopefully there's questions in the chat. And is someone going to moderate that?
I can moderate that.
Oh,
This is Darlene. We'll keep an eye out. Does anybody have any questions? Please remember to use the, there we go, the hand button. Dale Kiersted. We'll
Go ahead, Dale. You're on.
Hi, Jamie. This is Dale Kierst at DES.
Hi.
Could I briefly caught your discussion about chlorides, and the way I recall, there's virtually no real way to treat chlorides once they're applied to the roadway. And I think you mentioned the only way to really take care of that is the application process. Is that correct?
You got it. Yeah, I mean, there is ways to deal with chloride once it's dissolved, and it's called reverse osmosis. And so kind of that contrasts with what I said earlier. Most of our treatment systems in stormwater are passive and gravity fed, and we don't really anticipate doing things like reverse osmosis. I mean, what that would do on a treatment scale for the economics would be crazy, right? So the most economical, just way to address chloride is through the source control. And it's promising, right? We should, and so you got it exactly right. And but that's really the
So
advice.
To expand on that real quick, have you noticed, or has there been any research done to the difference between chloride applications when it's been, well, call it rock salt, versus the pre-treatment with brine solution, or are they pretty much the same?
No, they're not the same at all. And I think we haven't done those studies, but I think you'll find within the DES chloride control programs, you'll find that the pre-treatment with the brine, one preserves the roads better, so you have to apply less rock salt during the storm. So that pre-wetting with the brine means that the snow doesn't adhere to the road, so you have much less chemical that you have to put down. And the problem with the rock salt is I'll try to make a stab at it, but I think the estimates are that 30% of the rock salt it leaves the surface, because as it's applied it bounces and it just migrates to the side of the road. So yeah, I think this idea of using brine, which I know DOT is doing and many of the DPWs are experimenting with now, is a much better prospect for chloride reduction.
Thank you very much.
Ridge, you had your hand up. Do you have a question? Ridge Lemock?
Yeah, sure. Thank you. And I do notice one of my colleagues, Beth Ann McCarthy, has something in the chat, and this will give some of the shy consultant community time to develop questions, so it's not all coming from DES people, perhaps. But Jamie, first a comment. I thought it was very interesting and great that you mentioned many times in your presentation about maintenance and how incredibly important that is. And, you know, I tried to stress that a little bit in my talk. So it's nice to hear it from your perspective as well. In fact, one statement I wrote down is, I will take anything that you will maintain. I would hope we would put a little bit of limits on that, but I know what you're saying. But to a question, one related to maintenance, could you talk a little bit about what the expectation or what the requirements would be for vegetative maintenance, since a lot of our systems have a vegetation component, such as frequency, as to what their limits are for uptake, and then ultimately disposal, so we're just not reintroducing it. And then the other question or request would be if you could briefly maybe talk about the current state of testing of proprietary systems. What I'm getting at is, because we've had discussions, you know, laboratory testing versus field testing. Thank you.
Yeah, all right. So maintenance, our research shows that in approximately 3 to 5 years, unmaintained, these systems revert back to a state of performance, much like the state of doing nothing. So that is how important long-term operation and maintenance is. So, you know, the functional components basically are eliminated as the system clogs, especially filtration systems, right? At this, because the clogging occurs at the surface. So you could say that over time, an unmaintained biofilter turns into a detention pond because you're no longer getting access to the filtration aspects of these soils. And so maintenance is really important. For vegetated systems, we know that so, you know, and this is we're arguing right now, or I said there's, so, you know, the WOTUS rule, the Water United States rule is out there, and we're trying to get an exemption for structural control measures as being classified as waters of the United States. And so currently it's a gray area. So same thing with wetlands. Like we want structural wetlands to be classified with an exemption and not be thrown into statutory wetlands, because we need this ability to maintain these structural controls. Now, a natural wetland system, why don't we need to maintain a natural wetland system? Because we're not, you know, for the most part, we're not bonking it over the head with stormwater. In a structural stormwater control, like a horizontal flow gravel wetland, we're really pushing the limits of performance, and we're using the great function of wetlands and their ability to transform pollutants, but we're doing it in a very concentrated way. And so same thing for bioretention, and the maintenance sensitivity really increases as the hydraulic loading ratio increases. And that's why I mentioned, you know, Maine says no more than 20-1. I don't know that New Hampshire has a similar requirement on sizing, but we also size them statically, which also reduces the ability to, you know, load it, increase the hydraulic loading ratio too much. So what our target is to maintain the vegetation so as to keep the nutrient balance negative, meaning that in the reduction zone. Because over time, as we're pushing a lot of drainage into this small filter area, that nutrient balance occurring in the small area, especially with that vegetative uptake, is slowly tipping, right? So it doesn't really function like a natural wetland because we're really upping the hydraulic loading. So our recommendation is harvesting of the surface material every 3 to 5 years. And what we found in our research is that's about the time it takes with our climate regime for temporarily stored nutrients in the biomass to return to inorganic nutrient components through the natural decay. So if we're harvesting that material and composting it outside the system, and I say composting because, we're anticipating, especially with the push for street sweeping and leaf collection, more composting programs. So we're composting it outside the system. Now we can generate a nutrient source for, low risk areas like people's yards and gardens where use of those materials are fine. And we're giving that vegetation kind of a fighting chance to stay in the negative. And in fact, in our research, we saw that within 3 to 5 years, the performance of the gravel wetland really started to reduce. And that was our assumption, is that, wow, the balance is now being shifted because we have all this in-source loading from the decay of the in-system vegetation. And coupled with the large drainage area, that just becomes too much. So we would expect the same thing for other vegetated systems. The maintenance for most bioretention systems is selective harvesting, maybe every other year or so, and then that keeps the nutrient balance in the negative. With grass systems, a lot of times they're being mowed according to the conventionally mowing strategies that the municipality or maintenance facility is doing, and then we just encourage those to be bagged. And this is, what the funny component about that is, this is very different than what cooperative extension tells you to do on your yard, right? They tell you to mulch that, keep it there, create a thatch layer. But a yard is a yard has a hydraulic loading ratio of about 1 to 1. So, we have to separate the extra work that we're asking of these really environmental features that we're designing into our stormwater control measures and use the maintenance to give it a fighting chance. And that was the first question. What was the other question? I forgot it.
I will give, I don't know if I can see all the hands raised, but if there's not a lot of other questions, I'll repeat my other one, was to just talk about the testing of proprietary systems, the laboratory versus field.
Yeah, so so in this space of verification for manufactured treatment devices, there's really 2 programs. There's New Jersey, run through New Jersey NJCAT, and that's a laboratory testing protocol. And then there's the Washington State Department of Ecology TAPE program, and that's a field verification component. I will say, without incriminating anybody, while we don't set ourselves out to be a research and development field, meaning I get no financial benefit from any of the manufactured treatment devices that have been tested or are being tested at our facility, I will say that we do offer lots of enhancement strategies and advice through our testing, because we experience things in the real world with real hydrographs, with real world conditions that never get breached during laboratory testing. So, there's, in my mind, there's no comparison. There is a push for laboratory testing because it's easier, but I think the downfall of that is you get a less tested, less dependable treatment system. So, I would think that I could speak to the manufacturers that come through our facility, that they get a lot of good ideas from just seeing their system in action in variable conditions. When, the pollen releases, nobody tests that in a laboratory condition. And we use silica, which is an inorganic substitute for sediment. which has a pretty constant settling velocity. So there's no variability compared to the large range of organics that we see with variable settling velocities, right? So it's not, our settling velocity isn't 2.65. It's all over the place. So I would push for field verification. You could count me as biased, but I'm also experienced. I've been doing this for almost 20 years, and I see the disparity between a laboratory tested system compared to a field vetted system. I will answer Beth Ann's question, and I wish that we had more of a market, meaning that there were more manufacturers of these products. But I think it's a supply and demand.
Jamie?
Yep.
I'm sorry to interrupt you, but I'm not sure everyone can see Beth
Oh,
Ann's question.
I
Maybe
will
you
read
should
it.
read it into the record.
Beth Ann asks, can you talk about the availability to the public for water treatment residuals and for zero valent iron, and how to source it? And I have to admit that we're really in the beginning of this market. And so the sources are not well developed. That said, you go to any drinking water treatment facility, and we do this with UNH. We ask to take their alum sludge, and they give it to us freely and openly and as much as we can take. So the prospect for the development of a market, I think, is high. However, the source areas just haven't been well developed because the demand is emerging.
Okay, so in our last roughly 12 minutes remaining, we have two questions. The first is Kevin Nyan, and the second will be Jennifer Rezick.
Thank you. Can you hear me?
Yes.
Great. Thanks for the presentation. So Kevin Nyan, and I work here at DOT in the Bureau of Environment. And I just wanted to, make a couple observations and maybe ask for some input. So you'd mentioned that there's really no limit to what we can do in terms of what we have available to us for technology and that type of thing. I will, I didn't really, during the presentation, I didn't get I didn't hear the importance of maintenance. And so afterwards in your conversation with Ridge, to hear that, a well-maintained system is better than maybe a better designed system that isn't maintained, I could say we certainly agree with you. And to that end, I certainly agree with you. And to that end, I'd argue, that say the DOT, those who, aren't looking at stormwater treatments for a parking lot or something that's in one place, and we're looking at long linear facilities, and that the cheapest and most easily inspected and maintained systems are going to be the best, because like you mentioned, you can drive by a system and see that it's that it's not functioning and it's more easily maintained. So so I guess that's my my thought or opinion is there. And then how do we and I probably know the answer, but how do we respond? We're limited in terms of what we can do based on the budgets that we're given by decision makers. Oftentimes, some of the first things to go are these types of things, maintenance or whatever, in favor of replacing a bridge that's deficient. So, so I guess I just throw that out there as a consideration, and I think it's most important as you, the folks who are going to be putting together the new stormwater manual. I guess I'm concerned that perhaps the consideration of maintenance and long linear facilities would be left out of the conversation in favor of these more designed, say, subsurface systems that may have higher effectiveness when maintained properly. So, so I'm going to say there's a big difference, and looking for your thoughts and making sure that linear transportation is considered in all those discussions.
Yes, yeah, good points, and I completely agree, and I'm glad to have the opportunity to agree with your comments. We are considering a lot of the linear environment, and it's largely because of the recent consent orders that have been signed between Rhode Island DOT and Mass DOT. So all of these conversations have been happening just like this because they're being forced to retrofit their existing built environment. And so there's a lot of good information and good progress coming out of those efforts. Not least of which is this idea of impervious cover disconnection. And so it did get adopted in mass at DEP, but EPA has largely accepted it and has developed performance curves for it. And if you go to the retrofit manual, which I'll put a link to in the chat after I'm done, there's a whole section on impervious cover disconnection. And by impervious cover disconnection, I'm not necessarily talking about removing pavement, although that is an option. There are communities that are thinking about reducing the widths of roads and such, but I'm talking about the effective disconnection of that connected impervious into vegetated areas. Very, very applicable in a linear environment. And that is a codified BMP in the MS4, or that has largely been brought forward. I think it is in the New Hampshire MS4. I'm not sure. If it's not, it's certainly since been developed and will be in the next permit as well. And it's finding its way into other resource materials. So we hope to draw on things like that for the updated New Hampshire manual, or at least discuss them. So that impervious cover disconnection would be, it's based on the ratio of impervious to pervious. So very, very usable in the linear environment.
Great. Does that address your question, your comments, Kevin?
No, I appreciate the feedback and the response. Thank you.
Perfect. The next person is Jennifer Rexnet. I have allowed your mic. You're going to need to unmute yourself from your side.
Yeah, thank you. So I guess along the lines of what Kevin was asking, it seems like a lot of the measures that you were talking about work fairly well for site development. And if someone's developing a site, they have a vested interest in figuring all of this out to do that development. On a lot of our projects, that benefit is to the greater public, and the direct abutters don't always necessarily see the need for the development, nor do they like some of these treatment measures. So often this requires taking private property, and I've had multiple projects where we've either pulled scope back because abutters fought us so much on stormwater treatment, or where we've been forced into eminent domain situations. I guess kind of twofold. I'm wondering sort of a larger initiative so the public really understands the requirements, and they're not just hearing it from DOT saying this is required. I've had butters on a butter fight that, well, you don't actually have to comply with MS4. Well, we do. So I think some outreach there would be helpful. And I guess to echo what Kevin said, where we have a lot of these longitudinal projects and we don't have very much space of our own, looking at how we fit that in, and what would your message to that abutter be that says, I don't want a gravel wetland in my front yard, things that are less invasive and less intrusive, because sometimes we are talking about people's front yards or side yards and we're taking their property to do this. So I think that's an important part of this conversation as well.
Yes, yeah, well put. I don't have any political solutions to the lack of. We've always struggled in the stormwater side because it's largely invisible unless it floods out your house. So, if you have acute flooding issues, then you're keenly aware of the problem of stormwater. But from a water quality perspective, you don't see the nitrogen flowing in the storm drain, making its way to like a public water body and enclosing beaches. I mean, it's so there is an outreach and education component here. I don't necessarily know how to solve that. I think it's a very, very challenging prospect to change the hearts and minds of the general public, and you know, for the most part, we do see in general that people value the primary thing that they value is water and the quality of that water. You know, but these individual decisions, when you're talking about the commons versus someone's backyard, are a strategic issue. One of the other things I want to follow up on Kevin's comment is more and more we're seeing that in general, the long-term operation and maintenance has been left out of these facilities. And for the also along with that, if you look at the infrastructure, you know, linear foot for linear foot of pipe, the number of structures, we have significant amount of infrastructure in the ground. And yet we don't have adequate funding to maintain it. So I think there's been a short-sightedness historically in the stormwater world, where we have this legacy of neglect because we get the money to put it in, but there's no appetite or long-term funding prospect for the operation and maintenance. And we see that even with the Clean Watershed Needs survey. They're not including long-term maintenance as an expense, and that's a blind spot. I think where we see success is in the formation of utilities that treat this infrastructure in the ground much like it is an infrastructure with a useful life that needs maintenance and needs accommodation of long-term operation. So that is also that gets political quick, right? We can talk about the logistics of it and how smart it is and how smart that you know, users of that infrastructure would pay for the long-term operation and maintenance of that infrastructure. That's pretty logical. But when the minute you tell somebody, you know, we're going to increase the tolls or we're going to increase the fees, you know, operating this infrastructure to accommodate the stormwater infrastructure needs, you're going to get a lot of pushback politically. So, you know, we're in a tough spot. When I look into the crystal ball of the future, I see no way around maintaining and meeting our permit obligations and maintaining the long-term operation and maintenance of this infrastructure, other than developing a utility like we've done for the other water resource utilities, drinking water, wastewater. One could argue that minus the electricity inputs, we have the same amount of infrastructure, if not more, for drainage in the ground. So I don't expect that to be very popular with the abutters that are fighting you either. And this is one of the wicked problems I think that we're going to be facing. And we're going to have to develop innovative ways to bring everybody along.
All right, so this is Darlene, playing moderator for the moment. We are now 4 minutes into break, which will end at 10:45. However, we also have 2 more questions. So our first question would be from Mark, labeled as guest, and our second question would be from Sharon Monahan. And you're welcome to ask those questions, but the rest of you might want to take a quick break and be back for 10:45.
One person dropped their hand, so now we are with Sharon Monahan. If you want to ask a question, you have been unmuted. You're going to need to unmute yourself on your side. Sharon Monahan, you are unmuted on our side. You are going to, there you go.
I'm sorry. Okay. Thank you. I'm not a civil engineer and I don't deal with this. So I'm more in the layman's category, and I appreciated the previous question. I do deal with, I noticed that Shoreland came up with a manual stormwater treatment for homeowners that was very, very helpful, okay, in explaining and dealing with waterfront property owners. And it was an outreach program and it was helpful. I guess I'm wondering if you could do this. Our large projects deal with local planning boards, and they're just laypersons as well. So they do not understand, you know, the different stormwater remedies. If they understand it, then they can understand explaining things to the abutters, you know, that we spoke about. So could there be a simple stormwater management manual, just quickie things, layperson's terms of the importance of it for planning board members, and it can be available through the municipal association or the Office of Building and Planning. It just seems if they could do it for Shoreland, I just feel like there should be an ability to just educate through the governing boards who are approving projects and really don't know what the hell they're doing. Okay, so that's my question. Is there a ability to put out some sort of simple layperson's term for planning boards? And
Yes. So one of the benefits of originally being funded by the Near Science Collaborative, so this is NOAA funding, they had a very large focus on outreach. And so we developed annual reports, and I put a link to our publications and specifications, and I'll put another link to our latest annual report. And the objective of this report is to provide that resource. So we have probably 5 or 6 of these reports that I look at as sort of a consumer reports of stormwater treatment, stormwater control measures. And so the target was more municipal officials so that they could look at the range, and it compares how different devices work, because we recognize that early on, you know, somebody can really dictate the discussion in the planning board saying, oh no, my system, you know, it meets all the requirements, and it could be that it doesn't, and the community is going to kind of be on the receiving end of a poor performance. So we have developed some of those. I don't think it would meet all your needs, but you know, there is the homeowners BMP handbook that DES has developed that can also supplement you know, the need. So yeah, I would say what I have for you is probably our biennial reports, and you know, I would just breeze through them. They take on a different shape just about every time we produce them, and some might be easier to explain, easier to understand than others, but the target was for a municipal official. So we give you clear guidance of how the system works, what it looks like, and what the long-term expectations should be for its operation.
Yeah, and if I could just jump in here quickly, Darlene, related to Sharon's question, and I guess maybe a question to Jamie as to revising the stormwater manual, which is available online, the one that was written in 2008, Sharon. Volume 1 was intended as an overview. In fact, you know, table of contents, the chapter 2 is message for municipalities. I'm not sure if you're aware of that, but it does get technical further on, I guess you'd say, but it does provide some general overview of the stormwater world, if you will. So I just wanted to bring that to your attention. And Jamie, is the rewrite, are we going to just stick with like volume 2, the technical stuff, or is there going to be an attempt to address a question such as Sharon's?
Yeah, that is a good question. I think that's gonna be part of the internal focus groups where we figure, where we determine what the actual scope is. I think a 1-year scope would likely just address manual 2. But, we can certainly identify that as a need.
Okay, so that takes care of our question and answer for this first session. And we have entered into our break. We've got about 9 minutes of break left. We will start our next presentation, Temporary and Permanent Construction BMPs, at 10:45. So we'll see you all in about 9.5 minutes.
Good morning. Hope everybody.
Okay, we're back at 10:45 and we're going to start our next presentation. It's a pre-recorded presentation by Randy Shuey, who's a CWS, C-Spec, and certified soil scientist. Randy Shuey is an environmental scientist with over 30 years of experience working on environmental projects throughout New England. He has extensive experience with project management, environmental design and permitting, and stormwater consulting. Randy holds multiple certifications as a soil scientist and wetland scientist and in erosion and sediment control. He is also an approved trainer from several national and international organizations and has presented papers and training programs throughout the country on stormwater-related issues.
Good morning. Hope everybody's doing well. My name is Randall Shuey. I'm a certified soil scientist, certified wetland scientist, and certified professional in erosion and sediment control. I work for North Point Engineering out of Concord, New Hampshire, and I've been asked to do a talk this morning on stormwater management practices for construction sites, the design of those. Many of you in the audience have probably heard me talk before. I've been giving presentations on erosion and sediment control for probably about 20 years, 25 years now. We did one of our first ones at DES in Concord back in 2003. So that makes it 20 years with DES, and before that, some workshops. I have been doing training all over the country, and some of the photos you'll see are from some of the sites I've picked up, and others that I've got permission to use from various companies along the way. And what I want to talk about today is actually the design of these practices. A lot of times we're talking about inspections and we're talking about construction and working in those fields. But the design of it is really where everything starts. In a lot of cases, we'll see plans that come through that may or may not meet the requirements for actually controlling stormwater, actually dealing with erosion and sediment. And so we want to make sure that the plans are as good as they can be before the contractor gets on board, before the construction starts. So we're not playing catch up to the whole thing. So this whole thing starts, let's just see. In the 1930s, for erosion control, actually earlier than that, there's some evidence that bioengineering techniques, if you're familiar with those, go back thousands of years to China and stabilization of lands and changing lands in that region. More recent times, the US government got involved back in the 1930s when we had the Dust Bowl going on, when there was a lot of farm degradation, and they were noticing that the erosion was causing a decrease in the productivity of farmlands. In some cases, as in the picture you see on the screen from South Carolina, the technique for farming back then was to clear a field, do a slash and burn technique, clear the forest, and burn out the stumps for the most part, and then start farming. And the soils down there are extremely erodible, and in a lot of cases they were farming land for somewhere around 10 years before the productivity was just no good, and they would abandon the farm field and go off to another piece of land. So the result of that was to develop the Soil Erosion Service, which became the Soil Conservation Service, and then the Natural Resource Conservation Service, as it's called today, and as their mission and their goals have kind of switched around. A lot of the techniques that we use on construction sites were originally developed as part of agriculture, and a lot of the techniques we use to evaluate what kind of erosion we're going to have come out of that same study. So when we're looking at erosion, we want to look at the process of erosion. We need to understand what's going on. And the first thing we see is splash erosion, when that raindrop comes down at 35, 40 miles an hour, hits the ground, dislodges that soil particle, and we have those soil particles running in the water, making the water cloudy. The sediment runs downhill until the water slows down enough for that sediment particle to deposit out, and in which case we get deposition. Often, in the case of modern construction techniques, it's in areas we don't want it to be. It's in rivers and streams and wetlands, and we're having impacts on water quality. We're having impacts on the ability to use those waters. We're having impacts on wildlife habitat. And for all those reasons and many more, we want to try and avoid that and maintain the soil on the construction site as much as possible. So it starts with splash erosion. Those little raindrops form together in these films of water that form and flow over the land and get what we call sheet erosion, or sheets of water coming down in a very thin film. That films, depending on the soil type, is just enough to start picking up some particles. as it moves down slope, often within 100 feet, we're going to start to get these very small concentrated flows and form rills. Those rills get bigger and bigger, and eventually will form gully erosion. Once we get into gully erosion, we're going to need to start taking some much more aggressive techniques to control these. And the difference between a rill and a gully is typically rills are less than 6 inches. One of the anecdotal ways we talk about rills is something that can be taken care of with hand tools and some effort, whereas gullies are generally going to have to be done with either large machinery and or some kind of engineering to control that water that's coming down that hill. And what we want to do is just avoid all this from happening in the first place. We want to make sure our construction is done in a controlled manner, that we've planned for it, that we're going to work through this and not have issues with the downstream neighbors, downstream resources, and we're controlling everything as it goes along. In order to look at erosion and to figure out what's going on, we need to look at the different factors that affect erosion. And so we've got the big one, the one that we really can't control very much, which is the climate and weather. The location that you're working in is a big impact on it. If you're working in an area where, such as the Northeast, where a lot of the storm tracks will come up through New England, and so we get fairly frequent rains. Obviously, this past summer it's been a little dry, but you've seen in the last couple of weeks that there's a slow change in the weather pattern, and we're getting weekly rains at this point, and in some cases during the year we're getting more than that. And the time of the year is really critical. Understanding when you're going to be doing the construction and what you're going to have to do to get that construction to be done in a controlled manner is important. If you're working now and you haven't already started doing seeding and trying to get down your permanent seed mixes, you're probably at the end of that window to get anything to happen, get enough growth going that you're going to have stabilization. So you may have to look at other techniques. If you're working in the summertime and you put grass seed mix down, most grass seeds, most grasses go semi-dormant in the summertime. They tend to not grow very much. So if you put grass seed down in July, typically it's going to sit there until there's enough moisture for it to kick off. And then the construction period, how long is it going to go? Is it going to be a quick turnaround, 2 or 3 months, start to finish on a small project, or do you have a multi-year project? And how do you phase that through the different seasons? We have November coming up. November is often one of the rainiest months of the year. There's no vegetation growth in November. It tends to be the second mud season for loggers. So if you're familiar with that, you know there's going to be some issues. And we need to just be aware of those things. The second factor we look at is soils. When we're looking at soils, we can try and picture what we're doing with those soils in the construction site. And typically we have several layers of soils that we look at. The O and A horizon, which is generally makes up the topsoil layers, the organic layers, those soils that tend to be plowed off from a construction site and put into a big pile, and eventually somebody's selling them at Agway or Home Depot for you to put in your garden as topsoil. And the B horizons, that layer where due to chemical and physical weathering, there's some changes in the soils. And so there's either a change in textures or structure. And then the C horizon, which is the parent material, the materials that either glaciers or waters have laid down in the past. And those different layers will have different erodibility factors to them. And we can actually look at what those erodibility factors are based on the texture, the structure, the organic content, the depth of the A and the B horizon, or the soil together. And within there, we know that certain soils, when we're talking about loam or sandy loam or clay loam, those really what we're talking from a soil definition is the percentage of sand, silt, and clay. You'll see on the right-hand side, we have that soil triangle. And certain particles within there are very erodible. So the sand particles tend to be large enough where if they're going to move, they're going to need a lot of energy in the water to start moving, and they're out fairly quickly. The clay particles are so fine, and they have an electronic valence, a negative electronic valence, that they bind together, and because of that, they don't move very well. Problem with clays is they're so fine that once they do start moving, and it doesn't take very much, they don't settle out very quickly. It's very difficult to get them to settle out. And in between those, we have the silt and the very fine sand particles, which are the most erodible particle sizes, and those make up a good percentage of some of the areas, soil types that are shown within that red zone there: the clay loam, sandy loam, silts, and all those are soils that are fairly loose and will travel and not settle out until the water gets very still. So we need to know what those soils are. We can do that by the site-specific soil map that may have been done as part of an alteration of terrain application, or as a general guideline, we can look at the web soil survey, and we know that the web soil survey is a much larger mapping units. They're acres in size per mapping unit. But if you drill down through there, you can look and figure out what some of the subcomponents might be within that one soil type, and you can figure out what soils you may have. Ideally, the site-specific soil map and on-site test pits should be done to verify what you've got, so that you know whether or not you're going to have an issue with the soils on site before you get there. The next thing we want to look at is vegetation as a component for how much erosion happens. If we can keep vegetation in its place, it's going to go a long way towards it. Protecting the resource area, establishing new vegetation early on in the process are all key points. Vegetation helps by intercepting the rainwater, kind of acting as a little cushion so that we're not getting those raindrops pounding down on bare soil. It creates a resistant layer by the root mass that's in there and holds and anchors the soil in place. It retards the amount of water that's immediately starting to flow downstream. It's kind of acts that O horizon, an A horizon, that organic layer interface at the surface is going to start acting as a sponge and kind of slow things down initially. It allows for infiltration into the ground. The more vegetation, the better the root systems, the better the infiltration we have. And if we have no root systems, no vegetation on the site, it's very easy to get that surface layer compacted and get some quick runoff going on it. And finally, as we get the water starting to infiltrate in the ground, especially during the growing season, we get evapotranspiration. So the water hasn't moved very far down the watershed, and the plants are starting to suck up that moisture and get it back up in the air. And all that can be shown in this graph that we have on here, where the more cover we have, the less soil loss we have. And if you have 30 to 40% vegetative cover, so your grass is just starting to grow, or you've left some, you've gone in and you cleared the forest, but you haven't really stumped and grubbed it yet, that's going to go a long way to keeping soil in its place. And planning that as part of the construction phasing is going to be a critical part to making sure you're not going to have any issues. When we look at soil erosion, we've got a formula we often use called the revised universal soil loss equation, and it looks at all these factors. It looks at climate, it looks at soils, it looks at the cover type, it looks at the soil, the slope length, and the slope steepness, and that's what we're showing here on this slide. As you can imagine, longer slopes, steeper slopes, we're going to get more concentrated flows. We're going to get higher energy. The result of that's more erosion. Anything we can do to shorten up slopes and lessen the steepness through grading, through use of straw wattles or compost socks along the slope to help break that water up, will spread out the water, less concentrated flows, less energy, less erosion. The goal of all of this is to try and keep the soil and the soil particles as close to their source as possible. In an overall scheme of things, it's much less expensive for a project to do erosion control than it is to do sediment control, and it takes up less resources, less space on the site. So all that's pretty important. The main part of the talk here today is going to be on the stormwater controls, and we're going to go through. I'm not going to hit everything. This is based on the volume three of the stormwater manual for New Hampshire, and we've gone through some of that and looked at it. I'm going to talk about some of the design standards for some of the management practices and things that you might want to consider to augment those structures to make them function a little better. And I'm going to start off with just some background. In 1994, back in the early days of the National Pollutant Discharge Elimination System, NPDES, which basically started in '92. The study done down in North Carolina that showed that basically 50% of the erosion control measures were either never installed improperly, or installed and failed due to lack of maintenance. And while this seems like it may be a long time away, a long time ago for some people, it's really not that far away. And if we look at a more recent study from the EPA, they had up to 68 and 80% of BMPs on construction sites still not being installed properly, still not being designed properly, and causing issues, and not being maintained, which is a huge issue. And I'll tell you, from construction sites I've been to and from inspection reports that I've reviewed, there's always something mentioned in there about something that's not right. Silt fence is down, sediment is leaving an area it shouldn't be leaving. And in a lot of cases, from my understanding of the EPA inspectors and talking with them over the years, it's not the fact that you might have an issue on a construction site. It's the fact that week after week we see inspection reports with the same measures mentioned as not being repaired. The EPA construction general permit talks about timeframes for repairing those. I'm not going to go into a lot of detail or very much detail at all about that permit today. That's not the focus, but there's a whole bunch of information about timing on repairing, and they've really cracked down on maintenance schedules and what qualifies as a corrective action. And so you should understand what those are, and know that corrective actions often have to come back to the designers, the engineers, for some kind of additional design work input to see how things are going forward. So this is the manual we're talking about. Back in the 2000s, early 2000s, a group of folks got together and put together this stormwater manual. It's in 3 volumes. Volume 3 is what we're going to be talking about today: erosion and sediment controls during construction. This is the biggest part of protecting your resources. As a rule, from looking at these plans, there's a lot of thought, a lot of engineering going into the design of post-construction stormwater measures. And what we're trying to get people to understand today is that there needs to be that same effort gone into for the construction measures. This is the time period during construction when you're going to be under the biggest risk for water quality violations, when you're not going to meet water quality standards. And putting things in the right location, installing them correctly, making sure they're being maintained is really important. So that's where we're heading today. And we're going to be talking, we're going to be talking about what some people call best management practices. And I know I've done this talk a number of times. It's been some of these slides, people in the audience will recognize. Hopefully we'll have some different comments on them based on design instead of inspection and maintenance and general contractor information. And I don't want to bore you to tears with what's going on in these measures, but really it's important to understand it. And the first thing, you'll occasionally hear me slip up and say best management practices. It's been drilled into my head since at least the 1992 Rockingham Green Book, and probably before that, that these are best management practices. Well, there's really no such thing as a best management practice. A colleague of mine out of Syracuse, New York, Don Lake, who taught a semester-long college-level erosion control course, and has a really good book on that subject, always slapped his face whenever he said it, because they're not best management practices, they're management practices. There's no silver bullet, there's no one BMP that's going to work on every site for every reason, and you're going to have to be flexible enough to recognize when you need to change those things. So as we talk through these things, we're going to look at erosion controls. We're going to look at which are those measures designed to keep things in place. We're going to look at a little bit of overall planning and pre-construction thought that needs to go in the process. And we're going to look at runoff controls, those measures that are designed to move water through your construction site in a controlled manner, so that it's not heading to an area where it's going to just blow out your sediment controls, or it's going to cause more erosion, more difficulties as it's moving through your site. And then we're going to look at sediment controls, those measures that are used to help trap sediment in its place. We're going to talk about the standard things like silt fence and sediment traps and sediment basins, but we're also going to look at how you can improve those measures. And before we get to those, what I wanted to do was talk about some general practices you might want to think about, and some planning ideas to make sure we've got things moving correctly. So provide simple, well-documented erosion control plans. It makes sense. You might want to have a separate set of plans that just shows the erosion control, as opposed to trying to put the drainage plan and the grading plan and the erosion control plan all in one sheet. It tends to get very busy and very messy, and is a good excuse for contractors to say, I didn't know that was on the plan. I didn't know how to do that. I've also seen a lot of, I worked down in Massachusetts on a project where Mass DOT got into some trouble because they were overseeing a construction site similar to what happens in New Hampshire with resident engineers, and their construction plans had different sets, and the plans view was mentioned to refer to detail sheets, and the contractor didn't refer to the detail sheets enough, and there was some issues down there, so we had to do a training class down there for Mass DOT and the contractor, and nobody was happy about doing that, but we got through it. Details and dimensions for erosion and sediment control measures should be included. It's fine to put in a line of silt fence, but if it's critical to make sure you're covering an entire area, you may want to give dimensions on that. The specifications should certainly make sure that you're getting the right kind of materials to put in there. Pre-construction meetings are a critical part of any construction project, making sure that that as you're getting together, and maybe the engineer and the contractor are getting together for the first time with the owner and going to talk about the project, it's a perfect time to sit down and pull out the permits, whatever permits were issued, and talk about what the conditions of those permits are. Go through them line by line if you have to, and make sure that the critical parts, whether it be for endangered species or water quality concerns, or whatever the critical parts of that permitting that the design team fought through to get these permits and were incorporated into the plans based on working with the regulators. Make sure that the contractor is aware of why those are critical, and you want to try to get that all put together. And then have the contractor talk about what they're going to do to meet those conditions and make sure that everybody's on board with what's going on. Some proper planning techniques that we're going to look at or talk about here. Maximizing existing vegetation, keeping vegetation in its place, even if it's, you can kind of see in that bottom picture, although it's kind of small, there's trees left around, there's buffers left, well-defined buffers to protect wetlands, buffers left to, you know, is really as part of the overall landscaping plan. On this particular project, they wanted to keep some natural trees in there. It's part of the idea of how they're developing this site, but keeping that vegetation is not only going to protect the resources, it's going to add some value to the project overall, and only disturbing those areas that you can control. So the longer you can keep vegetation in its place before you're going to work an area, phasing a project is really going to be critical. Diverting offsite runoff and clean water from the immediate construction. Once you mix offsite waters and clean water in with your construction water, it then means you have to treat all of that water as construction water. So if you have 100 NTU water running down to your sediment basin and you've got this crystal clear mountain stream running down, and for whatever reason you're not protecting it, it's running onto your site, it didn't get diverted around the construction site, or some kind of just swale running down, you're going to have to figure out how to treat that. So if you've got 2-acre construction site and there's a 10-acre drainage area above you and you mix it all together, you now have 12 acres of stormwater that you're going to need to deal with on your construction site. Makes things very difficult. Provide additional erosion sediment control measures adjacent to environmentally sensitive areas. This means, and it's in the EPA construction general permit, when you're working less than 50 feet from a wetland, there needs to be extra steps taken. So typically they're looking for double rows of silt fence instead of a single row of silt fence. That means 2 silt fences spaced 5 to 7 feet apart. Making sure that you've got control of the stormwater so that you're not discharging directly into those receiving waters. Phasing larger projects, it's a requirement. And in some states, they make you do some extra steps if you're going to disturb larger areas. I know we've seen some projects come through with approvals from AOT where we're going to be doing, because of the size of the project or the complexity of the project, we're actually going to be required by AOT to be doing monitoring on those on a weekly basis. Plan phases according to the contractor. Really important. If you've got a contractor who's a small contractor, but it's a big project, you should not be starting off the project with saying, clear and grub the entire site and then put in the erosion control. That doesn't work very well. So you want to make sure that you're phasing it according to what the contractor can handle, according to what his equipment is, according to his methods and materials. Use temporary mulches and other methods to stabilize exposed slopes. Anytime you have exposed slopes that you're not working, you're going to need to have a time frame for when you need to get those covered, mulched according to the EPA requirements. Generally, they need to be covered within 14 days, not starting to stabilize at 14 days. So make sure that's done. Seed and mulch areas early and often. The quicker you can get things stabilized, the better off you're going to be. In the state of Maine, the Maine DOT, and I think they're still doing it, but it's been years since I've talked to them. They were buying slopes from the contractors as soon as they were met vegetated covered requirements, so that if anything happened on that slope or for any reason they had to go back in and work it again, Maine DOT would pay for that. And the result of that was they were winning awards for crossing of cold water fisheries. They were having sites that were meeting all the standards for the state and beyond. And then right now, and maybe if you're like me, when you get to the 1st of August and you're working on a construction site or you're planning for a site that's going to go over the winter, what are you going to do? How are you going to deal with the site? So as an inspector, when I'm going out to a construction site and I'm getting into August, I'm talking to the contractor about what we're doing for winter months. I was just on the left site this last week with the contractor, and he was confirming that they are not going to get seed mix down in time, that they're going to be putting down a lot of erosion control blankets in late October and November, and getting it so it goes over the winter. So those are the type of things you need to think about. I just want to jump back real quick and talk about construction phasing. Construction phasing is a critical and important part of any construction project. My colleague Jack Deering from Connecticut developed this boxing method where he would work with the owner about how to develop the construction site. Jack was a contractor for 60, 70 years of his career, and then he did some consulting work along the way as he got out of actual doing construction, working all over the Northeast. But his idea, which works on every site and can be for everybody's site, is what are the critical steps for the developer? What does he need to get done to make his project work financially? In this particular case, you can see the green area with the yellow boxes, which are townhouse condominiums that he wanted to get done first. Those were going to be part of the showroom. The black paving areas were going to be done early on. And then there was going to be access to phase work zone B, phases 1B. Part of that was going to be a borrow pit for phase 1. So some of it was going to be disturbed early on. And then they would start working that, and then they would infill in the middle as a third phase. And so you can see that over the long run, they were going to have a lot of thought in how they got this done. But before they were going into phase B or work zone B, there's already green grass coming up in phase A, and it can be done. We've worked construction sites where if you have the help, and I know that's one of the issues, but we've seen construction sites where every day at the end of the day on critical sites, on critical slopes, they would make sure that slope that they were working that day was loamed, was seeded, and had an erosion control blanket on it. And so by the time we got to the end of a 500-600 foot long slope, the grass was already germinated at the beginning of that project when we were wrapping it up, and everything was nice. And we're still doing that today on different projects as much as we'll allow. I once ran into a contractor up in Portland, Maine. They were working on a stream restoration project in the middle of the winter, and I stopped to talk to them, and they were putting down erosion control blankets. And I was like, "This is great. What's the plan here? What are you guys doing?" And they said, "Well, it's Friday. Friday afternoons is erosion control afternoon. That's what we do every Friday. We make sure the site's buttoned up for the winter, for the weekend. We don't want to get any calls. We don't want to have any issues." So they take the time to do that. And that's something that needs to get relayed to the contractor. That's something that needs to be written into the construction phasing, especially when you're working on critical projects on sites that are close to resources. A lot of these lakefront properties that are getting developed, they're tearing the entire site up. They may not be big lots, but there's a lot that could be done on it as we're going through it. Just real quickly, and this is part of the EPA requirements, I just wanted to mention to you stabilization deadlines. 5 acres or less completed no later than 14 days. So it's not in past presentations and past talking we've said, make sure you get it started within 14 days. And often we'd hear stories about contractors running a bulldozer across the slope to play with that game. They need to be stabilized within 14 days. It needs to be clear on the plans that that's the goal. If you're disturbing more than 5 acres, it actually is a smaller window because they don't want those areas, large areas, open any longer than they have to be. So no later than 7 days, you need to be completing areas that have been worked. That means that you're going to need a plan to have a crew that's doing erosion control, that's doing blankets or hydro mulching or whatever you're using on a fairly regular basis on the site, and not wait till the end of the project to try to stabilize the whole thing. And then final stabilization, EPA is 70%, I think, and Ridge might be able to clarify this. I think we're looking more like 80% in New Hampshire for good stabilization, good vegetative cover. So in order to get that sign off, that's what you want to look for. So that's the end of the of kind of the planning and pre-construction planning that needs to go into your thoughts about how this does. If you're a company that develops stormwater pollution prevention plans, all of this should be in your documentation. It should be made clear to the contractor what's going on. That pre-construction meeting is the most critical path to making sure everything's going to go as smooth as possible as you go down the road. So getting into actual BMPs, there we go. Construction management practices, gravel construction entrances, stone entrances. There's all kinds of names for them. There's several different details. This is one from John McCullough, who developed a program and it's still around, I think, called Erosion Draw. Typical details, and you'll find these like I think I was looking at the Connecticut Stormwater Manual recently, and these drawings popped up with the same graphics, different measures. But I'm sure there's a lot of people over the years who have used these and taken them. So they're fairly simple gravel construction entrances. They're also the center of the construction site, so you want to make sure it's well planned. You want to make sure within the documentation, within your specifications, that there's measures for stabilizing the area, that there's a place for the water to flow off of the stone. You want to make sure the stone is large enough to shake the large trucks, the 18-wheel dump trucks, whatever vehicles are going in and out of the site. The small Toyota Corolla inspection vehicle should have a little difficulty getting over a properly made gravel construction entrance. If you're driving into the thing and it's all smooth and it's almost a paved road, then there's definitely a problem. So here's one that's just been put down. You want to make sure that you've got a geotextile fabric underneath that stone. Otherwise, you're going to have the rock be pushed in through the soil underneath. And the old saying is 10 pounds of rock and 10 pounds of mud makes 20 pounds of mud. So it's going to get contaminated. There needs to be specifications in the reports for maintenance on these. It's one of those easy things that gets missed, that gets lacking. And invariably, as I'm driving up to a construction site and getting close to it, if I'm seeing tracking out into the road and it's extending down the road a ways, that means the construction entrance isn't right. And if the construction entrance isn't right, in my mind, what else is wrong on the site? That's kind of how I look at it. I don't know about the inspectors from DES when they're going out to a construction site, but it certainly starts to raise red flags that this site might need a closer look than it's getting. And in some sites, I will say that construction entrances don't function as well as they should. Maybe it's a muddy site, whatever. This particular site that we were working on from this photo, they also did two additional measures. One is they were on dry days, they were hosing down the trucks every time they left the site to get the mud off them. And then they also ran street sweepers twice a day up and down there. So depends on the area you're working in, but definitely something to look at. I want to jump into erosion controls real quick and look at the different methods and some of the more common methods that we're using for erosion control. One I want to talk about that's not getting used a lot and maybe should be used more when we're working on construction sites is tracking, making sure that we're getting the bulldozer running up and down the slope and getting good cleat marks in the slope. And then the different types of mulches. All these, whether it's a natural mulch, a rolled erosion control product or an erosion control blanket, hydro mulching, compost, wood products. I'm seeing more and more as different forested sites are getting developed. The loggers are leaving large piles of chips on site. The price of chips, it's just as easy to leave it on site than it is to haul to the wood production place wherever it's going. And so it's becoming more and more common to see that. And having an extra stockpile of that for instant cover to different to control to act in an emergency is really a good thing. So tracking is something that is done with a bulldozer. You're going to run it up and down the slopes. The specification is it's going to be used to break up the slope. Those cleats on the tracks of the bulldozer in this photo are making these little divots that's going to spread out stormwater. It's going to reduce the concentrated flow. It's actually going to provide this little microclimate for the growth of seed mix. And you can see in this photo where that bulldozer did the tracking. The hydro seeding on this job was, yeah, it was okay, but it wasn't great. And but they put enough seed mix down, and the seed moved a little bit, and it moved into the little cleat marks, and it started growing there, and it will spread out, and it'll get good cover as it's growing. It took a while to germinate. This is actually at the edge of the gravel road, so this is the, just like the shoulder of a road. This is where the vegetation is going to take the longest to get established. But it sat there. They hydro seeded it in July. It sat there till almost the end of August before it started to germinate. But when it did, it just popped, and it worked really well. So in this photo, I just want to point out, this doesn't look like a very long slope. It doesn't look like a very steep slope. It's not. But there's concentrated runoff coming down, and you can see that this is one of the things that happens when things aren't totally thought out. So it's a combination of not only these mulches that we're going to be talking about, making sure they're put in right, but making sure you understand how the water from the area above it's flowing. Often on filled and graded slopes, we get these rills forming. You can see at the bottom of the slope, this is actually a detention basin that we've got little sand deltas coming in. So there's going to be some remedial action needs to happen, and we need to make sure that that's controlled. So if we took straw and we put it through a straw blower and spread it out, and then took a bulldozer over it, that would be a great method to use. Straw anchoring, it takes the cleats of the machine and it makes those cleat marks that we're looking for to make that little microclimate, make that little seed bed, and it also punches the mulch into the ground and anchors it, so it's not going to blow away. If you just spread straw mulch on top of the ground without anchoring it, it may be an issue. In this photo, you can see the nice wetland behind the erosion control measures, and they've spread down hay mulch. This is going to work well as long as we get some moisture down on there and it starts anchoring itself. But if you've got high winds, that straw mulch will blow away very quickly. So you want to make sure that you're doing it, that you're somehow anchoring it. In the past, we've used, you can get just the plastic netting that is used in some of the erosion control blankets, and spread that over this mulch. It's a very inexpensive way to put it down. It takes a lot of effort. We're going to talk about plastic netting in a little bit and the disadvantages of using those. Spreading down hay mulch and then coming in with a hydro seeder machine with a tackifier in it, a glue that will hold this stuff in place is another option for that. When you're looking at the mulch, you want to, whether it's hay or I should have straw here, which does it need to be? In this particular case, there wasn't a specification. Hay mulch is much cheaper. Straw mulch is the residue from wheat and rye and various agricultural products. There's generally no seed in it. Hay mulch, you don't know what's going to be in it. If it's critical for your site, if you're working adjacent to a sensitive wetland system, you may want to use straw mulch. You may want to specify straw mulch, and it's important to know that. Wood chips and stump grindings, as I started to say earlier, are some of my favorite. I love wood stump grindings. They are long fiber materials. When you put them in that tub grinder, they make these long fibers that kind of knit together and bind really well. First time I heard of them being used was up in Sebago Lake area, part of the Portland Water District. and they put it down on some 3-to-1 and steeper slopes, and they had a hurricane roll through, and nothing moved, nothing eroded, no problems, worked really well. There's a whole bunch of stuff going on here, but this is wood chips that were used on a construction site. Wood chips tend to be a little easier to move than stump grinding, so not necessarily the best on sites where you're going to have concentrated flows. However, if you put them in a large enough berm, they will tend to mostly hold in place and not move. And eventually, as they start to decompose and those mycorrhizae from the funguses start to go through them, they actually start to bind themselves together really well. The disadvantage of wood chips and stump grindings, they really are a temporary measure in most cases because they won't allow vegetation to get established. So if you need to get vegetation established, you're working at the edge, such as this photo here, at the edge of a stream system or a drainage way, you really don't want that exposure. You want to keep the temperatures down in that area. You may want to get vegetation growing quicker rather than later. So another measure that's commonly used, and I'm sure a lot of us have spec'd it out on our plans, is erosion control blankets. They come in all different kinds of forms. Short-term erosion control blankets, long-term erosion control blankets, and high velocity. So the application that you're going to use it, how long do you need the blanket to last is critical. Are you going to be working this job and starting in May and ending in October, so that by the time you get into September, you're doing final stabilization, seeding, and mulching. In those cases, you can, and there's not a lot of water flow, you can probably get away with a straw blanket. If you have steeper slopes, you may need to use a coconut straw, which is going to last a little longer, but will hold up better to concentrated flows. We've seen contractors that have not followed the specifications and they've used straw blankets because straw blankets are cheap. And we've gone out to those sites where there was just a little bit of concentrated flow and all you see is plastic netting because all the straw has been washed out of them. So they absolutely do not hold up to any kind of concentrated flow. If you need something to last longer term, you're going to look at wood fibers or coconut fiber. These will last a year, maybe 2 years, depending on the density of them. They also come in more of a netting form, which is even more heavy duty. And then high velocity, which is turf reinforcement mats. These are either 100% plastic or partially plastic, and then with a coconut fiber or other material on them that allows water to flow over these at high velocity. They replace large rock up to 24 inches, depending on which manufacturer specifications you're using. So if you have an area where you don't want thermal pollution, where water quality is an issue, you want to get some filtering of stormwater before it enters a stream or a wetland, you can create these vegetative swales without rocks. Generally, they should be cheaper to put in for your clients and for the contractor. So that's one way to do it. We're going to talk so one of the issues that we're hearing, and a lot of engineers who are going through AOT and dealing with New Hampshire Fish and Game have been talking about or been asked about erosion control measures and which products are they using. So there's different measures out there that are more bio-friendly or more wildlife friendly than others. You can see on the photo on the left, that's a wood fiber erosion control blanket with a cotton or a string netting. It's very flexible. The netting is not woven together. The one on the right is more of a turf reinforcement mat type netting, and they get more aggressive than that, so there's no hole spacing. And those are designed to help. So turf reinforcement mats are used because they help anchor in the vegetation. They significantly increase the shear strength of that material and the vegetation. So the advantages of those, it's kind of a balancing act. It's one we really haven't worked out totally yet. You can see that this is a slide about the changes to the 2022 construction general permit. It says minimize impacts to wildlife by using wildlife friendly products as outlined by U.S. Fish and Wildlife Service. Those in the middle are again our nets and blankets that have a flexible netting on them. You can see the middle left where it's just kind of woven together, and as a snake or amphibian moves through there, it can easily push those aside and get through there, as opposed to the one on the right. This is becoming a huge topic. It's one I'm actually working on a presentation for, and we'll be presenting at the annual meeting at Nanners and at the IECA this year to talk more about this. We could spend literally a day talking on wildlife and products, and I don't think we have all the answers yet. There's some requirements that I'm hearing that people are being asked that don't, from an erosion control point and stabilization point of view, don't really fit in. So it's a balancing act that we're going to have to work together with the wildlife folks, and there's going to have to be some negotiations and compromises. We're not there yet. We're getting there. There's a lot of talk going on. This is kind of the hot topic right now in erosion and sediment control. So real quickly, just back to those turf reinforcement mats, they help hold the anchors, and this is the one that I'm struggling with the most. I love using this product, specifying this product, because we're going to get these nice vegetated swales. It's going to do that filtering that we've talked about. It's going to reduce the thermal pollution. If that slope that you see there was all rock and the sun was beating down on it, the temperature increase would be 20, 30, 40 degrees as compared to the vegetation that's coming through there. So much cooler, really lowering water temperatures. And so there's the balancing act. How do we make this work? I don't have the answers for you yet, but that's kind of where we're at and what we're working on. A little bit about hydroseeding. This is another method of stabilizing areas. Basically, hydroseeding is when you put the seed in a water tank and spray it on. Hydromulching is when you put a mulch in that tank and spray it on. And what's in the tank is often the mystery, and how much you need to specify or how much you specify or how much you leave the contractor is kind of one of those things where I think we're missing the boat if it's going to be a hydroseeded project. There are specifications for the type of hydroseed mulch you're using, and the seed rates, and the materials based on time of year, based on the area coverage, based on the slope steepness and the slope length, and how you're going to control all these things. And some are easy to work with, and some they're all fairly easy to work with, but some have limitations that you need to understand. I don't see a lot of specification of hydroseed and hydro mulches in projects. If we're not putting down erosion control blankets, what's the specification for those? And I just want to talk a little bit about that. So typically in the past, the cellulose mulch was what was first developed. It's the same material that folks use in insulation for houses. That cellulose mulch is basically blown into walls for insulation. And they use that same paper mulch. This is designed for very flat slopes. It's designed for areas where you're not going to have concentrated flows. You're not going to have long distances of slope. The next one above that is a wood fiber mulch. These tend to be longer fibers, and they tend to, like the wood stump grindings, they tend to knit themselves together a little bit more. The bonded fiber matrix is the next step above that. I actually call this you can think of this as the spray-on blanket. It's actually a three-dimensional blanket that you're spraying on. When you look at it in profile, it's got 1/8 of an inch thickness, sometimes thicker than that, depending on the rate of application. It takes a lot more effort to apply this correctly. It needs to be applied in 2 different directions, so it tends to be more expensive to use. The one thing it doesn't do is it doesn't hold up to concentrated flows. It will start rilling out with just a little bit of concentrated flow. And so with all of these, you need to think about how you're going to break up that water, especially on longer slopes. we're going to look at that a little bit later. The fourth type of material is called the high performance flexible growth medium, or FGM. The FGMs are similar to the bonded fiber matrices, except they have a polyacrylamide in them. And we're going to talk a little bit about polyacrylamides for water quality towards the end. But polyacrylamides are a group of chemicals that have been used for decades in the water quality, water filtration systems for water, drinking water. It helps take out all the cloudiness out of the water. It also helps trap all those fine particles together and settle them out. So they have this in that flexible growth medium. Within the state of New Hampshire, you cannot use flexible growth mediums within 100 feet of a water, surface water. And so you need to be aware of that when you're trying to spec these out. Most construction sites are going to be using one of the two middle ones, either something more than a paper mulch, something less than a flexible growth medium, generally, and it really depends on the site and the application. So steeper slopes require a more aggressive application. The length of time, just like erosion control blankets, the length of time you need it to last, whether it's a couple of months for cellulose mulch or you need to last over the winter and you're looking at bonded fiber matrix and the flexible growth medium. So you want to make sure that that's going on, and providing slope breaks on steeper slopes. Stockpiles, an easy way to stabilize those is to look at mulch, hydro mulch on them. If you don't want to have any, if you have a stockpile that you don't want anything growing on it, it's something that's structural fill or something you don't want to mix organics in with, then you can use, there are products you can use that will not allow vegetation to grow and will seal the surface. Like, I think one of the commercial products available is a dirt glue. It's a spray-on kind of sealant. It's biodegradable as far as I know. They used to, when I first started doing this work, there were some companies that were advertising these, and then there may be some areas where they're still doing it, but they were using petroleum-based products to help seal these. I don't recommend those. I don't think we can use those in New Hampshire. Other types of stabilization of stockpiles is just kind of making sure you've got them covered. So it could be plastic if it's a small enough pile. It could be using a hand seeder and a bag of conservation seed mix and just walking over the pile and getting some seed growing. That'll go a long way to make sure it's done. These need to be stabilized within 14 days. You need to make sure that just like any unworked area, it's got to be controlled, it's got to be protected. Just a little bit about seeding. I know in New Hampshire we've had some problems on some sites for construction where there was a seed mix specified because it was going to be an agricultural field and they want a certain grass seed mix, or it was going to be a wetland buffer or a critical area. So they had very specific seed mixes, and they had trouble with germination. When you're specifying out a seed mix, you need to make sure that that seed mix is going to grow on the soils you've got. And every single company that sells seed will tell you, if you ask for their help on specifying it, what does the soil test say for what you need? You need to know that is what kind of amendments, what kind of fertilizers, lime do you need to apply to get the grass seed mix that you want to go to germinate. And then you need to think about the timing of it. I talked a little bit about summer dormant season. Go ahead and put the grass seed mix down as soon as you can, get it mulched and stabilized. Mother Nature knows when it's time to get that growing. It'll be great. Same with late season, even right up until the snow. And I've heard stories of people seeding on top of snow, but right up until till the snow, you can put seed mixes down, and those seed mixes will start germinating before the road postings are pulled off the roads in the springtime. So go ahead and get the seed mix down any time of year. It's going to be a benefit to do that. Excuse me. The end of the growing season is kind of tough. We can look at different seed mixes and change the seed as we go into later into the season. Right now, you might want to be thinking about switching to winter rye. I had a construction project years ago where they put down winter rye in October, and it grew great in the springtime, but it did not grow in the fall. So winter rye is as I learned when I did a training class down in South Carolina, winter rye is the seed mix that they use in the wintertime when they can't get regular grass seed to grow. So it's a stabilization technique for cool seasons when other grass seed mixes or vegetation is not going to grow for you. But it is not going to grow after the frost hits. It's not going to grow in November. So plan on that. Plan on how you're going to control it. So that's it for erosion control. There's a whole bunch of information out there for all of these, whether it's the Stormwater Manual Volume 3, the EPA website has a whole bunch of information. You can look at almost any state. Most states now have erosion control manuals, and most of them are pretty much the same, but there are some differences. There's some other other places to get information, and certainly the manufacturers of a lot of this stuff will be glad to come in and do lunch and learns for your company if you want to contact some of the manufacturers and distributors in the area. A good way to get some additional training. I want to switch over to sediment controls. And sediment control is basically once that cloudy water starts moving down the hill, how we're going to trap it before it leaves the site, and what we're going to do to capture it. We can often tell when it's not working. If your measures are just not quite right. So this is a site that obviously there was some issues going on. They had some silt fence put up. The silt fence wasn't doing well. It doesn't look like it was quite put up right. I can see all kinds of issues with it. You know, where the two silt fences overlap in the left center of the photo, they really should be twisted together. And so that didn't work. They've got all this water going to the corner because all the low point in the grading is down in the corner towards the wire fencing that back there, and it's overflowing the silt fence. And so they put in some straw wattles to help do that. But straw wattles, the disadvantage of those are they're not 2 feet tall. They're only going to trap so much water, and they're only going to filter so much water. And both of these are designed to handle small areas. So if you have too much water going to an area, it's going to be an issue. And definitely there's a lot going on in this. And every time I show a photo like this, what I tell you as the engineers of the project engineers, when you're getting a phone call, because DES got a phone call and DES is calling you because you're the engineer of record, and they're saying, what's going on in this construction site? And you say, I don't know, I haven't been out there for a while because we weren't asked to do the inspections. When you get out to this site, you know, what you need to do is figure out why there's all this water coming to this corner, what you can do to stop that, why it's all cloudy, where the problem is, stabilize the uphill side, work on this downhill side all at the same time. The erosion control, keeping this sediment out of the water, is going to be a lot easier to deal with than it is to try and fix this. And so we're going to look a little bit about what we can do to make this work. Go back. Silt fence is everybody's using it. I haven't seen too many construction sites where there was no silt fence. I'm seeing a lot of compost socks used. The compost socks are now available in 10-foot sections or 150-foot section pallets, so you can go. You don't have to have the blower truck come in and make them for you on site, although you can, and there's some advantages of doing that. But silt fence is a fairly ubiquitous item in construction sites. You want to make sure a couple things. One is that the flow, the fence is on the uphill side, the stakes are on the downhill side. This is what your detail shows. that it's anchored in somehow, that your detail shows that it's anchored. There needs to either be trenched in or use some gravel if you're on a hard surface and you can't anchor the fabric in. I've seen on pavement where they want to use silt fence. They've actually used construction adhesive to help glue the fabric down to the pavement. Worked okay. You want to make sure that there's no issues with it. It's fairly easy to put in. It's fairly easy to do it wrong. And it's fairly easy to design it wrong because we're not looking at what needs to happen for it. So the design of silt fence is maximum steepness of 2-to-1 slopes. You don't want it on any steeper slope. You don't want to put it at the base of a 2-to-1 slope and hope that that's going to work. You need to set it off a little bit from that. The maximum length between silt fence is 100 feet. So as you're coming down a slope, when early on I mentioned that concentrated flow starts to occur within about 100 feet. So they want to prevent that concentrated flow. You want to make sure every 100 feet you have the proper silt fencing. When you're designing for silt fence, you want to look at the small sub watersheds and where water is going to flow, not just at the beginning of your construction project, but as your construction project changes. You may need to have additional silt fence put in on the interior part. You want to make sure it's parallel with the contours and it's set back from the toe of the slope. Here's a great example, courtesy of Don Lake, where the silt fence is a good 10 feet off the toe of the slope. There's some larger stones that have rolled off the side, but they stop before they hit the silt fence. There's a good buffer behind it to protect the neighbors. So they're not going to have an issue there. It's running parallel with the contours, so we're going to make sure that everything is working right. You want to make sure that the ends of the silt fence are turned up and so that the water's not running out and running around it. There's different things we can do with silt fence. Again, you can see in this photo, we've got silt fence with hay bale combination. This is a Massachusetts DEP general requirement when you're working at the perimeter of your site or adjacent to wetlands. You can see that we've added another silt fence on the uphill side. There was too much water going to that lower silt fence. And the easy solution was just to add a second silt fence to capture some of that water up in the watershed. We can use things like J-hooks. These are two things going on here. First of all, the J-hook is used when your silt fence has to run down the slope instead of along the slope, or instead of along the contour. So this creates these little mini watersheds where trapping water as it's heading down. That's the first thing to notice here. The second thing to notice is this is the Walmart specification. Walmart was the poster child of what not to do, and they became the poster child of what to do. They're probably the toughest company to work for erosion control. And you can see that they have wire fence stakes. They have a 6x6 wire fencing backing up all their silt fence, no matter what. If you don't have it exactly like this, they get really mad. I believe instead of 6 feet apart, those stakes are 5 feet apart. And the question is, how does it work? It works pretty well. Here we're ponding almost 18 inches of water. And while there's water spilling over the top, the silt fence hasn't collapsed. It seems to be trapping what it is. And while we still see some cloudy water on the downhill side, if this is Georgia, this is how it works. It's all yellow water anyway. Hay bales, not the best thing to use. It's hard to get them in correctly. You need to trench them in the ground. It takes a lot more effort. You need to make sure they're butted correctly. Generally, where I see the best use of hay bales as a perimeter control is when they're used in conjunction with that silt fence. I really like this idea. When you've got a small area to work in, you don't have enough room to put in multiple rows of silt. This is really a way to beef it all up and make sure that you're not going to have any issues. In this little picture, you can see they dug a little hole right before there, just a little added area. This is a culvert replacement, and they just wanted to make sure they were trapping all that water and it wasn't getting out into the lake where this culvert was being replaced. Straw wattles, fiber logs, all really great things. The issue with these, and everybody using them. The straw wattles will initially allow a lot of water to go through them fairly quickly. They're fairly porous. The advantage of them is that they're going to spread the water out. And so if you're using these on hill breaks, it's going to work well. The disadvantage of all of these straw wattles, compost socks, whatever you're using, is they're going to be limited to how much they can store water they can store behind them by their height. And you need to plan on that. So you may need to space them closer together than you would, say, a silt fence. And the best way to use this type of material is to make sure the area above it is stabilized. So mulch it as quickly as possible. Here's a good example of using the wattles across the slope and acting as slope breaks so that we're breaking up that water as we come down a very steep slope. This is a landfill project where they need to get grass growing, and they didn't want any. There was no chance of going back and fixing it after the fact. It was just going to be too steep. Again, it's easy to see whether lack of maintenance and what happens with just a little bit of rain and sediment buildup. These take a lot more maintenance if you're going to be using them. Compost socks are great. If you're using a blower truck, you can put them through the woods and make them fit pretty well. There are specifications in all the manuals on how to put these things in. They don't vary very much. I'm not going to go over it. You can find those pretty quickly. When you get into areas such as this, and you're looking at multiple rows of compost socks, this is a Massachusetts DOT project. They were just having problem after problem, and Mass DEP and Mass DOT often butt heads, and Mass DEP says just fix it, and so they just keep throwing material after it and not really considering how it's going to be fixed. So I'm going to jump ahead a little bit here because we're running out of time, and I want to talk a little bit about inlet protection, but we're going to run through this one fairly quickly. Inlet protection I look at as kind of your last opportunity to trap sediment before it leaves site. You should look at this as your perimeter of your site, unless it's running to your sediment basin. But it's better to trap it here than to try and clean out the drainage culverts that are put in after the fact. Jetting those out becomes very expensive. And if this is draining to a municipal separate sewer system, you better make sure it's clean water as possible. Often these are designed with, let's call it homemade materials. So we put a geotextile fabric around some concrete blocks, and we put some stone around that. And what happens is the whole structure that we put in there is so tight together, and the stone's small enough that as we get larger flows, the water starts flowing around those areas. So we need to make sure that we're getting the water into the basin. We're designing for the flows, we're getting there, and what's working. If we can get an area where in these photos we can see catch basins that are in a sump kind of area, and we've got acting as like a sediment trap almost, then we can protect that catch basin and allow water to pond around it before it's discharged. Manufactured ones work really well. The only issue I have with these, especially in existing roads, is they tend to raise the grate just enough so that some of the water doesn't get in here, and you're going to send the water downhill to the next basin, to the next basin. So making sure that you're designing for what fits your construction site is important. Making sure that if you need to use a manufactured one, that it's spec'd out to properly work, and it's going to fit in there properly. Moving on, I want to talk a little bit about dewatering and sediment bags. We're seeing more and more of these used. They work pretty well. As you can see from this photo, or hopefully you can see on the lower part of this, even though it looks like it's not bleeding sediment, there's some cloudy water out of this. So we need to make sure sediment bags are set up away from resource areas. They shouldn't be set up at the edge of the lake. They shouldn't be set up in wetlands. There should be a buffer and a filter to go through it, whether it's straw walls, compost socks around it, in addition to further treat and trap the water. And when these things start blowing up like a balloon, you should be telling your contractor they need to replace them. They are fairly inexpensive compared to the overall construction projects. They run about $200, $250 a piece. You pull it out, you put a new one down, you're good to go. So we want to make sure we're doing that. Real quickly, sediment basins and sediment traps. Basins are for large areas. They tend to have a structural outlet. They should have some kind of surface method of skimming water, a surface skimmer. They need to be engineered. They're collecting drainage from large areas. It's not something that I, as an erosion control specialist, feel qualified to design. Anytime we get into structures and engineering and possible dams, that's when the P stamp needs to come out, and that's when I'm relying on the engineer. Alternatively, sediment traps are for smaller areas, and they're really easy to construct. They can be as simple as taking a bulldozer and making a depression in the ground. And we've done it on construction sites to just trap water so it's not all going to the perimeter of the site, and there's no structural outlet. Sediment basins should be designed according to a certain design flow. EPA says a minimum of 3,600 cubic feet per acre of drainage area. We're looking at surface skimmers on them. We want to make sure they're going to be designed properly, that you're considering the stabilization of that basin, that you're not sending water to it before it's stable and able to receive it. Generally, that means you're speccing out erosion control blankets in that basin on the sides at least. And you want to make sure that you're speccing out that it gets maintained at least half the at a maximum. When half that capacity is filled, then you're filling it, then you're cleaning it out. Two examples that we often that I've seen. One is your traditional one with a riser pipe and perforations. I'm still seeing these used. The disadvantage of these is that they're collecting water from all the different levels, and as the water is dropping down or flowing into that outlet structure, it's getting dirty water from the bottom and cleaner water from the top, and you don't really have anything to if you have cloudy water coming in and it's not all getting trapped out, it's going to be bad. Alternatively, we can use baffles and skimmers, and we can try and just collect the water. We can try and make a longer flow path through the basin with those, and then we can use a surface skimmer to collect just that top level of water. Here's an example of a typical basin. You can see some issues with unstable slopes, some deltas of sediment going in there, and a structure that's probably not going to do the best for trapping it. Sediment traps, just real quick, they're areas designed to capture water. This is Lake Louise down at New Bedford Regional Airport, called Lake Louise, somebody's wife, I think. There was a catch basin in the middle of this. They didn't want the water to go anywhere. They were having problems with discharging water into wetlands. So there's a catch basin somewhere in the middle of this ponded area, and they just closed the catch basin off, and it acted as a sediment trap. There's no outlet for that. So it worked pretty well. You can make sediment traps any way you want. You can fit them into small areas. You can put you can put stone in to make it to help filter some water out. I want to show a baffle real quick, and I'm going to play this video. So this video is showing some. It's at the North Carolina State University test site, their stormwater center. They're sending down dye in a stormwater that they're pumping in, or water that they're pumping into this basin. You can see the water's coming down. It's very agitated as it hits the basin, and then it's really just going through that. This is a coir netting, and it's getting very calm. It's spreading out. It's really using the whole basin. It's, rather than having a slug of water go straight from the inlet to the outlet, this allows the water to spread out, and a good idea to use in your basins if you're having trouble. This is one way of augmenting your basin. This is the surface skimmer. This is the Faircloth skimmer. There's a couple others on the market, but this is the easiest one I found to get a hold of. This is the original. I'm not promoting them as the only one, but this is one I've used in the past. It plugs into It plugs into the basin. You can see in the upper photo, it's sitting on the ground in this vegetation basin. And it just sits there quietly waiting for the water to come. And then you see in the lower photo, when the water level rises, it rises with it, and it's capturing just the first top half inch of water, collecting the cleanest water in the basin, and making for the cleanest discharge possible from the basin. Very quickly on flocculants. Flocculants, I talked about them earlier. They're used in water, drinking water. They've been used for literally generations now. They are a material that you can use to mix in with your stormwater, and it will basically combine with the soil particles and help those particles get larger and settle out. So if you're working with very fine sediment particles, clays and silts, and it's just not settling out, this is a method of doing it. There's two different types of flocculants, cationic and anionic. Cationic needs a special permission to use from EPA because they are hazardous to fish. Anionic are not hazardous to fish in general, depending on what material are. You need to have the soils and the sediment that you're going to be discharging tested. Most of the manufacturers, they run the tests and tell you you need this amount of flocculant per 1,000 gallons or whatever it is. And you need to know the flow rate, and there needs to be some mixing and then some settling within it. If we go to the next slide, this is another example. These are just different logs, flocculant log, compost logs, coir logs, straw wattles, and all they did was sprinkle a little bit of the flocculant material on here. This whole swale is about 60 feet long, and what they're going to do is they're going to grab samples as they go through. The water goes over these things. At each log, they're going to grab a sample, and if I go to this is the result. So in 60 feet, they went from the left-hand water to the right-hand water. Now, not totally clear, but you know, if you had some settling time additional afterwards, you could clean that water up pretty quick. And this is some very fine sediments, very high silt and clay content in the soils around Raleigh, North Carolina. So it's something we'd like to see be able to use more. You need, if you're going to use this on a construction site, you need to have permission from DES. You need to apply to alteration of terrain for a special permit to use this, and that permit gets reviewed by the Watershed Bureau, who gets input into it. It's a very time-consuming process, and one that needs to be straightened out a little bit. And we don't have time to go into it anymore, so we're not. Runoff controls really quickly. I want to talk just briefly on shorefront properties, because I've seen a lot of this lately, and we have gotten several calls over the past couple of years on projects that were not well constructed. We're having some issues, and what was happening is they would go in and clear a site per the shoreland permit, and they would put a big structure, the house, right in the middle where the best view of the lake is going to be. And as you can see on this photo, what's left, if you can see my mouse moving, is that there's just these little areas on either side. And what tends to happen is we've got, if you look at these two photos, say this is the width of the property, we have all this width that the water's been running down historically and just kind of meandering through this forested area, or maybe there's been a little cottage on the site and hasn't been an issue. And then somebody comes along and wants to put in a house, and all of a sudden that area that they used to be able to run through, which the water was spread out, is all of a sudden concentrated along the foundation. Q equals AV, that's a formula that all the engineers know. The water quantity equals the area times the velocity. And if you decrease the area, so you go from this wide area here to this area here on either side, you're going to increase the velocity. When you increase the velocity, when you increase that velocity, you increase the erosion potential and the erosion forces in there, and you start having all kinds of issues. We could do a whole couple of hours just on that alone. We don't have time. One of the ways you can stop that is using check dams. These are designed to slow the water, make it go down in a controlled manner. You want to make sure that they're the elevation of the toe of the slope is equal to the elevation of the top of the one down for spacing requirements, so that you get these nice ponded water elevations between them. If you use a coarse stone to kind of hold the thing together, and then a finer gravel on the uphill side, it can act as a filter. Really wonderful things to use. This not so much. There's also kinds of problems with using hay bales as check dams. The EPA since 1992 has said hay bales should not be used as check dams. They're not to be used in concentrated flows. They don't work well. There's all kinds of issues as you go through with it. Real quickly, one of the things we've been dealing with, and I think last week there was some discussion on water diversions and pumping. You want to make sure they're properly planned for your project. Generally, when we've worked on stream crossings projects, we're not only doing water diversion, but dewatering within the construction site. And they're two different things. You need to make sure both are working effectively and they're designed properly. It takes some engineering to think this one through. You know, the engineering has gone through to design the crossing, whatever you're doing. That same effort needs to be done in the stream channel itself. The one thing we're not going to cover today is good housekeeping. That's a whole nother topic, a whole nother thing we can get into, but just know that this is part of what your responsibility is for developing a stormwater pollution prevention plan. This is part of your erosion control, things like spill kits and making sure you have the proper materials on site and that you're taking care of what other are potential pollutants. I would like to just wrap up by saying there's no magic bullet. We've rushed through this stormwater presentation. I have done entire days on this and gone into a lot more detail. We don't have time for that today. Make sure you know what your toolbox. Always try to be expanding your toolbox and know that there's alternatives. If something's not working, find your local CPESC or look up the folks at some of the distributors for the erosion control products. They'll be glad to help you out. There's a lot of tools in the toolbox, and if we just use the same one, two, or three, we may be setting contractors up for problems. Keep the plan readable. Make sure that it's clear. There's a lot that goes into designing these things. It needs to be understood by the contractor. Just a real quick story. We had a contractor doing a commercial redevelopment, one big box to another big box. And the first thing he did is go in and totally tear out the existing drainage system, which was the last thing we wanted him to do. But it wasn't clear to him, and we didn't have a pre-construction on that meeting, on that project. And when he went to town, we were fighting an uphill battle the rest of the construction project. But so you want to try and avoid those. It's very easy to get the lessons learned. We could have a whole conversation on that. Design considerations. What's the construction goal? The construction goal for the owner, the construction goal based on the environmental permits that have been issued, and the construction goal to make sure that the engineering plans that are post-construction stormwater management are going to be built properly. You've got to incorporate all that work into your thought of your erosion control so that you're not screwing something up for a later construction phase. Site conditions are really important. We talked about soils. We talked about water running through the site, changing soil conditions and site conditions as the construction goes from steep slope to level parking lot and how you're going to manage that, and making sure all those things are working together. If you, I think it'll go a long way to working well. I'd like to thank you all for putting up with me this morning. I am pre-recording this because I'm on vacation, and I'm sure there's probably some questions that have come up in the chat or however we're asking questions. And I would like to say if I can get a copy of those questions, we can respond to all of them put together a response to those and email that out to all the participants. I thank you all for your time this morning, and I look forward to seeing you at a future workshop. Thank you.
Okay, so
Darlene,
as a
I just wanted to
follow-up,
say,
yes, Ridgely?
yeah, Randy emailed me. He said he's available, so he's, I guess, gotten online.
He's here with us.
Okay.
Mr. Shuey has joined us and has mentioned that he is available to take some questions live. So we can take questions here for a bit. Ridge, do you want to handle this last? Because you've got the wrap up from 12:15 to 12:30 also, Ridgely.
I'd be happy to. I just need to turn on the chat and see if people are raising hands.
At this point, just remind folks, if you have a question that you'd like to have answered either by Ridge or Randy, please use the virtual hand raise button. Chris Albert has the first question.
Go ahead, Chris.
Can you hear me all right, Randy?
I can hear you. Can you hear me?
Oh yeah, thanks. I think for all of you, between Randy and Ridge and most of all of you, I think you hit it hard, pretty good as far as silt fence. I would hope all the agencies and erosion control specialists, we can start kind of phasing out silt fence. It was a great technology of the 80s and 70s, but it doesn't work now. I'm seeing more and more issues with aquatic organism passage. These long-term perimeter controls, as far as disconnects, like you said, Randy, we're the guys 3 years later that are going out with the hammer and X-Acto knives, ripping them out of the woods after everyone's all long and gone. So I'm hoping with some of the new BMP manuals and some of the other science coming out, we can probably try to stop kind of keying out the using silt fence. Thank you.
Yeah, I guess I would agree with that. I think silt fence is going to have its place in areas that we need to just contain that water. And it really needs to be designed properly, and it needs to be spec'd out that it's going to be removed. And I think that's kind of where we're missing things. We as the designers don't see the end project a lot of times, and it's a problem. And there's no final sign off from us that the project was completed.
Our next question is from Dale Kiersted.
Hi, Randy. I just want to expand on something you hinted on earlier. Winter stabilization. I've actually had some interesting discussions where somebody has gone out and sprayed seed, say today or a week from now, and then the AOT rules and the CGP both have requirements for winter stabilization, but they're actually getting no growth between now and then, or very little. It depends on the season. There was one year we had fantastic growth right into November. But if you spray seed today, you get no growth, then you're not meeting any type of stabilization requirement. And winter stabilization may still be required on top of the seed you place, so you don't end up with erosion during thaws or spring melt.
Yeah, that's right. It needs to be planned for the full winter. And if you're doing seed mixes and getting things established, the guideline has been after September 15th, you're looking at more temporary stabilization. And then further into the year you go, the more temporary stabilizations you need to do and the more heavy duty to get over through the winter.
In the absence, if anybody's got, Dale, do you have another question?
No, I'm sorry. I was trying to turn my hand off.
Okay, we don't seem to have any other questions at this time. Ridge, do you want to wrap this up with another closing statement? Is there anybody who has a question just so Ridge doesn't have to talk? Mr. Evans, Jonathan Evans.
Go ahead, Mr. Evans.
Hi. I guess I was wondering, I'm not sure if this is for Randy or Ridge or both, but does DES or AOT kind of discourage or recommend the use of a particular type of hydro mulch near sensitive waters, like a protected shoreland, adjacent to a lake or fourth order stream, something like that?
Well, what I can
Well, I
add
know
to that, I welcome Randy's input. I think Randy touched on that. I can't say we have a specific hydromulch. We just have prohibitions on those with polyacrylamides within 100 feet of surface waters, as Randy said. Other than that, I don't believe we have any recommendations, if you will.
So there's not like necessarily a blanket like prohibition of the use of any hydromulch within within that protected shoreland, correct?
Yeah, the only prohibition is that polyacrylamides, and most of those are the flexible growth mediums. And if you're trying to figure out if your hydro mulch is the right one, you would need to read the specs on the product you're applying and talk to the manufacturer. But it's kind of the Wild West with mulches right now.
Okay,
Ridge.
thank you.
Ridge, is there a fertilizer component in those hydromulches that might run afoul of the Shoreland Protection Act?
It's, as Randy said, there's a mixture. They can have fertilizer. They don't have to have them.
The fertilizer is usually added separately.
So it would be advised not to add the fertilizer separately if you didn't want to run afoul of the fertilizer prohibition in the Shoreland Protection Act, or make sure that the spec matches the nitrogen, phosphate, and release rates found in the Act.
Right.
Okay, thank you.
Are there any other questions?
We do not
Okay,
currently
well,
have any other questions.
thank you, Mary Evel. Okay, then, well, I guess at this point, I'd just like to take this opportunity, one, to we failed to mention it on last Friday's webinar, to thank our partners at EPA. They provided a grant that helped support the planning and development of these two webinars. So thank you, EPA. Certainly want to thank all of you who attended. We had great attendance, somewhere between 125 and 150 participants for the two sessions. I'd like to thank all of our presenters, especially today, Randy and Jamie, and my colleagues, Carl Benedict and Dale Kierstead, who presented last Friday. And appreciate, once again, all of you attending. I hope you got something out of it. And in closing, I guess I will say, maintain your health, maintain your construction sites, and maintain your stormwater facilities. Thanks, everyone. Have a great weekend. Oh, I think people are signing. I saw Tracy Tarr, last minute question.
Yes, Mr. Houle had his hand up as well.
No, I was just looking for the clapping function, but I don't think Microsoft has added that yet.
Well, we're down to 35 participants, so thank you, everyone.
Auf Wiedersehen.